Okay, I think it is time. So, welcome to the third and final day of FCBS workshop for college chemistry students and teachers. And today also we have three lectures. Today's sessions are chaired by Professor Subi Jacob George. He doesn't need an introduction to the Kerala college audience, especially the teachers, and most of the recent students know him. He's received this year's Shantisaru Bhatnagar Award, and we are all proud of him because he is part of FCBS for from 2003 onwards, and all the FCBS, and he is our alumni also. So we are so happy. And over to you, Subi.
Yeah, thank you, Joshi, for the very kind introduction. Welcome everyone to the last day's program of FCBS. As Joshi mentioned, we have three speakers, and all the three speakers are from three different institutes. So yeah, that's very unique. And so without wasting Borges' time, let's go to the first talk of today's program. And that is, it's going to be delivered by Dr. Boche Gowde, who is the senior scientist at NIIST Trivandrum. I am sure, again, Boche does not need introduction to this audience. He is the well-known polymer chemist. And so he did his PhD at University of Pune and postdoctoral research at Toyota School Foundation, Japan. He is extensively working on various types of polymers, polymer block copolymers, polymer composites, many, I mean, like various aspects of polymer chemistry. He's extensively contributed. And so it's very appropriate that this year, as all of you know, we are celebrating the 100th anniversary of polymer chemistry. So I think it's very appropriate that Boche Gowde, an expert in kind of polymer chemistry, is giving this talk where he talks about the present challenges and exciting future in this field. So before I again invite him, just let me tell you that he has contributed extensively to polymer chemistry. He has been recognized with many awards. I will just mention a few of them. Like in 2016, he received the MRSI medal. And especially for the contributions to polymer chemistry in 2018, the Society of Polymer Science India has given the Professor Kaushal Kishore Memorial Award. And then he has been, RSC Polymer Chemistry Journal has chosen him as the pioneering investigator. And so this year he got the Fellow of the Royal Society of Chemistry. So his work is well appreciated and recognized. And I'm sure he's an ideal person to deliver this talk when we celebrate this 100 years of polymer chemistry. Boche, please.
Yeah, thank you, Professor Subi, for your kind words. Let me thank the organizers, particularly Professor Bala, Dr. Joshi, and Professor Rezi, all these things. I thank Dr. Suresh Das and Professor Rao for wonderful opportunities. This is my third talk in this FCBS series. I'm attending the FCBS for the last 10 years. And also I had a wonderful opportunity to see and interact Professor M.V. George many times because we were sharing the same floor. My office was next to Professor George's office. I dedicate this talk to Professor M.V. George. So I used to get calls sometimes. We used to discuss or interact for half an hour, 1 hour also sometimes. And he was really a great source of inspiration, not only for me, for many youngsters in the country. So let me go to my talk. I'll be mainly talking about the 100 years of polymer science. I'll talk about a little bit glorious past and also what are the present challenges and exciting future. So before going to my talk, I will just show one slide showing like how this polymer science has evolved as an interdisciplinary discipline. So basically, we need like a knowledge of chemistry, physics, and also engineering, particularly chemical engineers or technologies. And this subject is truly interdisciplinary, and polymers are truly miracles of chemistry and engineering. When you see the polymeric materials offer great value proposition to consumers in terms of maximum functionality at lower cost. When you compare with any other material, so polymers are cheaper compared to the other materials. So initially for 10 to 15 minutes, I will talk about the glorious past of polymer science. So before even knowing what is polymer science, there are like two wonderful technologies were evolved. The first one is the development of rubber. There are like two inventors, one from United States, Professor Goodyear, and Professor Hancock from United Kingdom, UK. So both of them, they discovered the vulcanization and they independently patented this process. As Kerala students and teachers, they don't need any introduction on the rubber, latex, all these things, and the importance of vulcanization. But you can see the discovery of this vulcanization has created a wonderful material, and it got applications in many areas. And in this graph, you can see the consumption of rubber worldwide from 2000 to 2019 is really like 1,000 metric tons of material has been used. So this is a first example. And the second example, again, without knowing the science, technology has been evolved and industries has been started. The second one is Leo Baekeland. So he has discovered a material called phenol formaldehyde resin. So the trade name of this material is bakelite. So in the name of Professor Baekeland, so it was named as bakelite. So he started this General Bakelite Corporation in 1910 to manufacture this product. Basically, this is the first synthetic plastic. Before that, also some polymers are known like cellulose and other natural polymers. When it comes to the synthetic polymers, so this is the first polymer. So intention of discovery of this polymer was a replacement for shellac, that is a natural resin secreted by a female lac-bug on trees. So, and the main constituents of this material is like a allylic acid. So, and this was really exported to different countries from India. So, in order to replace this, Professor Leo Baekeland, so he has done this reaction like phenol and formaldehyde with different compositions. And the structure of this material is still not known because it's like a getting cross-linked in different directions, and it's a highly insulating material and having high chemical resistance. And it got superior thermal and mechanical properties because basically it's a thermoset. And initially, if you see the olden switchboards and olden like telephones, all those materials, all those products were made using phenol formaldehyde resin. So this is the interesting part, like without even knowing what it is, like how the polymerization occurs, the products were there already in the market. Then it comes to the birth of macromolecular chemistry. The concept was introduced by Professor Hermann Staudinger. So when he tried to discuss about this polymers, so many organic chemists, basically, they did not accept this idea. So because there was a controversy, I have shown here in this cartoon, you can see basically the monomers are like these paper clips. So in order to show that, he has shown this kind of a model where you can stitch this paper clips with a covalent bond. Then basically we can form a polymer like that. But most of the organic chemists, they were always debating that this is not like a long chain molecule or a long chain macromolecule. Basically, these clips aggregate like this to form colloids. So this was one of the debates, and it took really long time. Initially, Professor Staudinger started working on different natural polymers such as starch, cellulose, proteins, all these materials. So later he started synthesizing the polymers such as polystyrene, polyethylene oxide, polyoxy, methylene, all these things. And he has demonstrated the like a higher molecular weight of these polymers. So he used to believe that these are like a long chain macromolecules and they are rigid, they are not flexible. This was the belief of Hermann Staudinger. So he won the Nobel Prize. Oh, sorry, I will just minimize this. He won the Nobel Prize in 1953, and he is the founder of the first polymer journal, that is Macromolecular Chemistry. Now it is known as Macromolecular Chemistry and Physics. And this was the first paper published by him that's written in German. So it was published in 1920. That's why this year we are celebrating the 100th anniversary of the discovery of polymer chemistry or macromolecular chemistry. Then American Chemical Society and the German Scientific Society, they have identified the Freiberg as an international historic chemical landmark. And there on the flake, they have written like this, like a Professor Hermann Stedinger between 1926 and 1956 carried out his path-breaking research on macromolecular chemistry in Freiburg. His theories on the polymer structures of fibers and plastics and his later research on biological macromolecules formed the basis for countless modern developments in the fields of material science and biosensors and supported the rapid growth of the plastic industry. So this was the birth of the polymers. So later, Professor Hermann Mark, he is from Austria. He's again trained as an organic chemist, and initially he was working on natural polymers such as cellulose, rubber, all these things. And he has discovered that these macromolecules or the long chain molecules so can crystallize and they can organize into the crystalline lattices and lamellas. So this was the discovery, and his work has really convinced the researchers about this macromolecular concept. At the same time, there was, as I already mentioned, Professor Staudinger was believing that these are rigid molecules and it's difficult to bend. And where the Professor Hermann Mark, for the first time, he has demonstrated that basically these are flexible chains. And there is a possibility for the folding of the chains, but he has not discovered the folding. But he has mentioned that these are flexible coils due to the hinder of bond rotation in polymer backbone. This is what he has discovered. Later, Professor Andrew Keller from University of Bristol, UK. So he was the person, he discovered the chain folding. Basically, these are macromolecules. When we look at the dimensions of the lamellas or the crystals, which are angstrom and in nanometer length scales, there was again a debate like how these macromolecules will organize into the lattices or lamellas. So Professor Andrew Keller, he has proved that the chain folding occurs, and it's almost like 60 years back he has discovered that concept. So Professor Mark, he has shown that these polymer chains can form unit cells and space groups, that is cellulose and rubbers, all these things. Even if detailed molecular structures are not known, he proposes that in polymer, lattice forces are comparable to intramolecular forces, and the entire crystallites behave like a large molecule. This is what he has proved. And apart from that, he is the first gentleman who has started a graduate program in polymer science at Brooklyn Polytechnic Institute in 1946. And he has designed the curriculum on polymer science. So though his discoveries are very well recognized, so he was not awarded the Nobel Prize. Then it comes to the birth of the rational polymer synthesis, Professor Carothers. So he trained as an organic chemist with Roger Adams. And initially he was hired as a faculty at Harvard. Later the DuPont moved him to Delaware to do fundamental research on organic chemistry and polymers. And he is the gentleman who discovered like many polymers, mainly based on the polycondensation. So he has published a series of JACS papers. In that area, he lived for a short time, but still he has published more than 50 JACS papers on esterification, polyesterification, and also on diacetylene, on different kinds of systems. And he was the one who discovered the first synthetic rubber, that is chloroprene, and the trade name of that was neoprene. So that was the World War II that time, and there was a huge demand for the like a fiber kind of materials. So he was asked to make like a materials which are similar to the silk. So he has discovered nylons and polyesters. Unfortunately, he could not see the applications of those materials. So despite his great success in this polycondensation chemistry, so he always used to feel that he has not accomplished much, and he was running out of the ideas. And because of that, he has committed suicide in 1937. So he was short-lived. Unfortunately, because of that, he has missed the Nobel Prize. So then comes to the polyolefins. So most of you know, today we are debating a lot about this material. Ziegler and Netta independently, they have discovered the catalysis for the polymerization of ethylene and propylene like gases. So they have independently, they have used titanium-based material as a catalyst, and aluminum, organoaluminiums as co-catalysts, and they have synthesized polyethylene and polypropylene. And today, you know, if you take the usage, world plastic usage, almost like more than like 60% of material is only from these two materials, polyethylene and polypropylene. Later there were like so many developments. So unfortunately, these are the two wonder materials. Because of this, there are like a lot of opposition also on polymers because of the waste management that I will discuss in detail in the coming slides. But even in India, our Honorable Prime Minister in last year Independence Day speech, so he requested the country to completely eradicate the single-use plastics, so mainly which are based on polyethylene and polypropylene. But unfortunately, because of this COVID pandemic, again, that was not possible. The complete ban on single-use plastics was not possible because the materials what we are using today for personal protective equipments and also for face masks, all these things are mainly based on polypropylene. So we have to specially thank Professor Ziegler and Netta for these wonderful materials. So then it comes to the not the discovery, but on the concepts. Professor P.J. Flory, he is the physical chemist with extraordinary mathematics skills. So he worked with Carothers at DuPont and developed the basic principles of polymerization, kinetics, and also the statistics of molecular distribution, polydispersity, chain transfer. All these concepts they have introduced, and they have also developed theories to understand the polymer crosslinks or networks, where the gel formation in the polymers science also widely studied, and they have significantly contributed in understanding the conformation of the chains, the crystallization behavior, elasticity, the glass transition, hydrodynamics, different kinds of properties of these materials. And he has written like a wonderful books on polymers. The first one is Principles of Polymer Chemistry. Even today, this is like a Bible for the polymer science students all over the world. This is the one was used for teaching purpose. And he has also written another book, Statistical Mechanics of Chain Molecules, in 1969. This is also a wonderful book. So he was awarded the Nobel Prize in 1974 for all the contributions he has made for the polymer science. So then it comes to the recent Nobel Prize, that is conducting polymers. So Nobel Prize was given in 2000. Professor Alan Heeger, Professor Alan McDermid, and Professor Shirakawa shared this Nobel Prize. So earlier it was believed that polymers means insulators, but they have discovered like a different kinds of systems, and they have shown the by doping these polymers, so the polymers can conduct. So that they have demonstrated. It has to be noted that none of the conducting polymers are intrinsically they are conducting. So we have to dope it. So today we are talking about like different applications like photovoltaic cells and also transistors, data storage, like different kinds of sensors, supercapacitors, actuators, all these things. So where we are using these conducting polymers widely. So, but there are several challenges in using the conducting polymers, though it's very easy to solution process them. In certain cases, we have to chemically modify some of these polymers to make them soluble. Otherwise, the solution process is very, very easy using this, and you can generate like a films like very similar to newspapers. So in that area, and there is like a problem with the toxicity, because when we are adding dopants, basically dopants are toxic. So when we are processing, there will be an issues. Unfortunately, the melt processing is a little bit tricky using the conducting polymers because of its viscosity issues and stability issues. So still, it's required to work on developing the new polymers where we can like melt process, and also intrinsically we can make them conducting by using different synthetic techniques. So apart from that, so far whatever we have discussed are basically a covalent based polymers. Those are robust in nature because the bonding is the covalent bond. But there is like a the recent developments are the non-covalent polymers or supramolecular polymers. For example, the chairman who introduced me, Professor Subi, is working in this area. There are like several groups, research groups are actively working, including Professor Uday Mehta, Professor Ajay Ghosh. There are several people, they are working in this active area, the dynamic area. So these polymers are dynamic in nature. Basically, they use non-covalent interactions such as hydrogen bonding or pi-pi interactions, all these things. And these systems are really coming up. Again, Professor Jean Mary Len, he won the Nobel Prize for supramolecular chemistry. And now there is a lot of progress in this area, even on supramolecular living polymerization, supramolecular block copolymers. And the major advantage is here is, so in the previous cases, once you form the polymer, it's really very difficult to break down it into the monomers. But in using these dynamic systems, we can make them like a reversible assembly or disassembly very conveniently. And you can find many more applications of this kind of systems in near future. So this is all about the greatest discoveries. But when it comes to the golden age of polymers, you can see some most of the polymers were discovered from 1900 to 1950. So you can see here like bakelite, LDPE, polymethyl methacrylate, polyurethane, polystyrene, Teflon. All these polymers were discovered in this region. But after 1950 only, the growth of the polymers has started. The major materials, whatever I was telling about, the high density polyethylene, polypropylene, styrofoams, polyamides, they are all discovered from 1951 to 1985. Even after 1985 also, there are some materials based on new catalysts such as syndiotactic polystyrene, all these things. So mainly most of the polymeric materials were discovered before 2000. So when we see from concept to the market, so you can see this table. So in certain materials, certain polymers, for example, nylon 6,6 and polyethylene, polypropylene, after their discovery, it has gone into the market within 3 years because of the properties of those materials and its easiness for processing of these materials, all these things. But there are some materials took very long time also, like polyethylene naphthalate and polyvinyl chloride. They took almost 27 years or 24 years from concept to the market. So some of the slides I have taken from Dr. Sivaram's presentation. Particularly this slide I have taken from Dr. Sivaram's presentation. I acknowledge Dr. Sivaram for this. So these are all about the glorious past of the polymer science. So when we look into the present challenges, so if you see the today's scenario, the global production of plastics is around 360 million metric tons. So out of this, 170 million tons is going for packaging applications, and it's generating around 60 million jobs all over the world. So the business value is around 1,200 billion US dollars per annum. And the waste, what we are generating out of this is around 250 million metric tons. Unfortunately, out of this 250 million metric tons, 75 million metric tons is mismanaged. So it's completely going and mixing with the environment. So in oceans and environment. When it comes to the India, so India's production was around 100 million metric tons in 2019. So I have given the composition here. So out of this material, so majority of this material is going for packaging applications, around 39%, and this is causing the real problem to the environment. So, but when we look into the number of jobs and its business value, this is very impressive. This polymer industry grow from zero to present capacities in about 60 to 65 years, the faster ever growth of any industry in the post-industrialized world. But it's like a challenge to handle this 40% of the waste plastic. So let us look into it. So basically, we have to understand the impacts of plastics throughout their lifetime. The first challenge is, as I already mentioned, so when we produce a product out of the polymer, so out of this 14% is going for recycling. Means again we can use them. So again we can generate the value-added products out of this. So without losing much of their properties. So here the weight average molecular weight is shown. So basically before the degradation, we can reuse them. That is around 14%. So and another 14% is going for making fuels out of this using different kinds of catalysts. 40% is directly going for landfilling, and another 32% is mixing with the environment. This is basically causing a lot of problem. And when we started using the polymers, basically under the sunlight, they degrade. When they degrade, they form like a microplastics or nanoplastics. So in order to address this challenge, we need to develop analytical method to study how these microplastics or nanoplastics are formed, and and on what time scales it forms. All these things need to be studied, and it has to be recorded. And also we need a dedicated research is required to properly understand the factors that form the microplastics and nanoplastics. This is basically the challenge one. When it comes to the challenge two, the sustainability is the more important thing. Science to enable sustainable plastics is the second challenge. So we need to design the polymer structures that can be disassembled and controllably broken into the smaller subunits such as oligomers and monomers, which can be reused effectively. For example, if you take polymethyl methacrylate, there it is possible to unzip it and to get monomer, and we can repolymerize it. But it's not the same case with polyethylene, polypropylene, all these things. So here maybe to some extent supramolecular polymers may help, but still a long way to go. We need to understand like the formation of robust structures using that supramolecular chemistry. And also we need to find new plastics which are capable of maintaining desirable material properties even after recycling. So that is very, very important. Basically, what happens when you use the material, after some time, the polymer will degrade. As a result, your a molecular weight will be decreased and the properties will be decreased. But you have to find out the polymers, even after the usage of the polymer, the degradation should not be too much. There should be a possibility for the self-extension, chain extension, or self-healing process with the usage of the material. And in the third case, in the long term, the manufacturing of polymers may need to be decoupled from the use of virgin fossil fuels. So this is very, very important. This I will discuss in detail later. And the third challenge is closed loop plastic recycling. So when it comes to recycling, so we need like a chemical technologies that are related to improve the labeling and identification and separation of waste plastics and composites into single component and pure polymers. So this is one of the greatest challenges. So you can see when you buy a plastic product, so this kind of labeling has been given. For example, the code, if you see, for example, if you purchase a bottle or a plastic product, there this will be printed. So from that you can identify this is a particular material. So there are like a 7 class of materials coding has given. The first one is polyethylene terephthalate, second one is high density polyethylene, polyvinyl chloride, low density polyethylene, polypropylene, polystyrene, and also the bisphenol A based polymers such as like a polycarbonate and epoxies, all these things. So here really still we have to educate the people so that we can sort out the polymers very effectively and it can be sent to recycling. For example, if we mix PET with polypropylene and if we recycle it, we don't get anything. You can't reuse that material. So that's why educating the public is very much necessary. And also we need the technologies to discover this depolymerization of some of these polymers using new catalysts and also new processes. And reactions for polymerization and depolymerization that are closer to equilibrium should be investigated. That's very, very important. So that we can have that kind of a sustainable nature and appropriate to process waste plastics to recover the energy they contain. So this is also is one of the major area which is coming up. New catalyst has to be discovered to convert the waste plastics into the fuel. So these are all regarding the thermoplastics, but the real challenge comes with the thermosets because we can't melt or we can't dissolve the thermoset systems. So one of the greatest challenges today is recycling of the thermosets. At present, the thermosets are grinded into the small powders and they're again mixing with a new products before curing, so that they are basically speeding up the curing process that has been done, but still a long way to go to understand the recycling of thermosets. The another challenge is the control of polymer degradation, understanding and control of the polymer degradation. So here we need to understand the cause and extent and time scale of polymer degradation reactions and to understand the impact of degraded products on the environment. This is because there are like a wide varieties of polymers. Each polymer behaves very differently. So each polymer, the chemical contents are very different. So it's necessary to understand after the degradation what kind of products are coming out, and that has to be recorded. And research is needed to develop materials that are both recyclable and environmentally degradable. So this is one of the very, very challenging issues. But at the end of the recycling, they could degrade into the non-toxic products. So this is also very important. Environmentally degradable polymers will need to be competitive in performance and cost. So this is basically, we already have several biodegradable polymers such as polylactic acid, and there are like different kinds of aliphatic polyesters. They're all very good biodegradable polymers. Unfortunately, the cost of those polymers are very high when you compare to polyethylene or polypropylene. So that's why replacing those polymers with a cheap biodegradable polymer is a challenging aspect. And also there is unlikely that a single material able to deliver all properties for all kinds of applications. Consequently, we need to generate a library of materials which are environmentally degradable. So these are some of the challenges. But when it comes to the science, here also there are so many challenges. As I already mentioned, so Professor Andrew Keller discovered the chain folding behavior. But when you take like a small molecule, there the crystallization, for example, if you take, the crystallization happens very easily because the monomer or the small molecule can migrate very comfortably to the crystal growth front, and it can form a 100% single crystal. But when it comes to the polymers, so polymers are macro molecules and long chain molecules. The transportation of the polymer chain to the crystal growth front is a challenging aspect. So basically, because of long chains, there will be a lot of entanglements will be there. There are tie molecules. That's why this is not an easy process. Till today, there is a big debate that whether this process is a single step process or a multi-step process. So this is what I was mentioning. Though the polymers are long chain molecules, they can fold into the lamella as shown in this cartoon, and this lamella sizes will be typically in the nanometer in dimensions. And in order to understand that, we need like a different kinds of tools, how this polymer folding behavior or polymer crystallization process is happening. So Professor Gus Strabel from Germany, he has proposed a multi-step process. So he has shown that before the random melt is going into the stabilized lamella, there will be like some kind of a mesomorphic layers which are similar to the liquid crystalline materials. Unfortunately, still this is not accepted by many researchers because of the non-availability of the experimental tools to understand this kind of a behavior. So because X-ray will not give any information, only we have to depend on the spectroscopy. So to some extent, FTIR, it is possible, but the time scale of this process is very, very small. So maybe I will discuss when I'm talking about my work a little bit on this concept. And the second scientific challenge is, so for example, if you take like a polyethylene, so it's like a simple aliphatic chain. So there we can produce different kinds of materials depending on the molecular weight of the polymer and the kind of branching we have. We can have LDPE, we can have LLDPE, we can have HDPE, we can have ultra high molecular weight polyethylene, which is having very, very high molecular weights. So processing these polymers is really a challenging issue. For example, in the case of LDPE and HDPE, we can use like a conventional processing method such as injection molding or blow molding, all those things. Whatever the carry bags you are using is based on LDPE or LLDPE, and the paint containers on such kind of applications, you can use high density polyethylene. Basically, it will have highest crystallinity because that's more of linear in nature. But when we take the example of ultra high molecular weight polyethylene, because of the chain entanglements, it's not that easy to process using the melt processing because it builds up very, very high viscosity. So the one of the greatest challenges is how we can process this high molecular weight polymers without the chain entanglement. So for that, at the moment, so we're using like a gel spinning method. So when we use gel spinning method, basically we have to dissolve this polymer in some solvents like Decalene or paraffin or such kind of solvent. We have to spin that, then that solvent has to be evaporated. The petrochemical based solvent has to be evaporated. And this has to be again done at slightly higher temperatures. So you can see what kind of like a environment we are using. Like we are polluting the environment by evaporating large amounts of solvent in order to get highly oriented fibers of this polyethylene. And this can be very effectively used for bulletproof jackets, all these things, because you see that the chemistry is same. In every case, you are repeating it is same. But when it comes to the application, it's completely different, because how you are organizing this polymer chains is very, very important. But the entire process is unfriendly to the environment, and we need to discover like a new processing methods. For example, if you take the lessons from nature, you take an example of spider silk. So the spider's silk fibers are formed at room temperature using water as a solvent. You see, it's like a very eco-friendly, and the process is done at room temperature. There is no energy consumption also. So basically, you know, like a though the water has been used as a solvent, these fibers are completely hydrophobic in nature. So you can see from this picture also. There are like, and this fiber is stronger than steel and it's tougher than Kevlar. So we need to learn some of the chemistry from this kind of nature, so that we can avoid such kind of like a processing methods, as well as the synthesis. Again, it's like a tedious to generate the ultra high molecular weight polymers. Very recently, from Japan, the bagworm silk fibers has been extracted, and they have shown that this is much stronger and tougher than any other natural fiber which is seen in the environment. So because they have studied very systematically, and they found that the hierarchical arrangement of this monomeric units, or the repeating units, are the cause for this outstanding properties, and that properties will be retained until the fracture. So that is the beauty. So we need to learn several things from the nature, and we can even understand like how best we can organize this monomeric repeating units to generate the high quality or high strength fibers from the like a synthetic polymers. So there is like another challenge. If you take an example of polymer nanocomposites, to the best of my knowledge, for the last 3 decades, several polymer groups they have been working in this area on polymer nanocomposites. So people use different kinds of nanofillers. For example, 0-dimensional nanofillers, 1-dimensional, 2-dimensional. But unfortunately, when it comes to the practical applications, so it's difficult to get the reproducible results because of many challenges. So because the interface between the nanoparticle and the polymer should be good, then only we can have like a reproducible result. So for that, whatever the inorganic nanoparticles or the materials we are choosing, we have to modify them effectively, and we have to use them with the polymers. So if the interface is very good, then only we can have a better mechanical properties. And also we, for example, in certain cases, when we are using such kind of modifiers, when we are processing, unfortunately, some of them, they will degrade. So when they degrade, the modifiers or surfactants, whatever we have chosen, so again, the interface will become very bad. That's why it's very difficult to produce the reproducible results using such kind of nanomaterials. So, so interested people can see very recent perspective, which is written by Professor Sanat Kumar to celebrate the 50th anniversary of Macromolecules Journal. There are several challenges, still a long way to go. In certain cases, it's done very effectively, but still a lot of challenges are there in this area. So another area is like the energy research. So here also a lot of work has been done. In India also many groups are working. So mainly the major advantage of this polymer based solar cells are the devices are like these are flexible in nature, lightweight, and there are several other advantages. So for Toyobo, a Japanese company, recently they have showed like a 25% of power conversion efficiency for organic PV cells. So using their own material. So that is not known, but a lot of work has been done in tuning the band gaps and also synthesizing new materials to tune the band gap. There are several aspects has taken care. But in this case, in most of the cases, again, the morphology of the donor and acceptor molecules, how we are organizing these donor and acceptor molecules basically determine the efficiency of these materials. So for this, the ideal morphologies are basically the morphologies which are shown in this cartoon. You can see here a red and blue polymers are there. If we can have the morphologies of donors and acceptor molecules like this, where the domain size or periodicities are 10 to 20 nanometers, which is matching with the exciton diffusion length, then we can get the better efficiencies. Unfortunately, controlling the morphology is one of the challenging issues. particularly when you take like a conducting systems, which are having like a donors and acceptor units. So it's very difficult to organize them like this because of their chain folding behavior is not as simple as like other semi-crystalline systems, because a lot of complexity is involved. Then there will be a competition between the crystallization and microphase separation that leads to basically disorder morphologies as shown here in this cartoon like this. So there are several groups working in this area. Again, Professor Mukundan Talikat is like he has synthesized wide varieties of systems using donor and acceptor containing block copolymers, and so far they could achieve only 2 to 3% of efficiency. But if we can chemists and physicists and engineers, if they come together and if they organize them into like a very uniform morphologies, and these are like ideal materials for this kind of applications, particularly for flexible voltaics and battery applications, for fuel cell applications, all these things. So this is another challenging area where a lot of focus has to be given. Then I will talk for another 5 to 10 minutes about the future of polymer science. So if you check basically, so so wide varieties of polymers has been synthesized. It's not that easy to replace the existing polymers, but still we have to see what kind of polymer synthesis is required, because we have seen very linear systems and very robust systems. But we need to go for like a complex systems in order to get the multi functionality. So, and also another issue is the depolymerization of waste plastics. And as I already mentioned, like organic electronics and OLEDs, the sustainability is more important, and we have to focus mainly on bio-based and renewable materials. When it comes to the applications in mind, we have to focus on energy, healthcare, security and informatics, and defense and protections. So I will give a few examples. So when it comes to the polymer synthesis, finding new polymers to replace the existing polymers such as polyethylene, polyamides, and polylactide is like an enormously challenging task, because there are well-established techniques are there and the processing methods are there. So it's not that easy to find. So there are like several developments has happened in this area, like many discoveries has happened, like ATRP, raft techniques, and different kinds of techniques to synthesize like different kinds of systems like block copolymer, star polymers, all these things with multifunctionality. There are like people explode a lot. I will show some of those examples also. And discovery of the metallurgy catalyst quickly convinced the community, especially the commodity polymer community, because initially people were thinking that only the linear kind of systems are possible. But again, using this kind of catalytic system, macromolecular different macromolecular architectures has been discovered, and they found different kinds of applications. So in this aspect, again, many groups are working on precision polymers. Means basically it's like a sequence control polymers. For example, if we want to insert a kind of a grafting or like a side chain at a particular number of carbon, we can do it very effectively. And also we can go for like a iterative synthesis of monodispersed step growth polymers to having polymers with dispersity close to 1. And also we can also think about the new synthetic approaches for the living and controlled chain growth pi conjugated systems. So that's like a very, very important for all these energy applications purpose. And we also need to understand like a molecular self-assembly methods applied to synthesis of polymers with novel topologies. So if you see the basic polymer chemistry, basically it is done by mainly two techniques. One is like a step growth polymerization or chain growth polymerization. So in this case, in the case of step growth polymerization, basically we need like a two different kinds of monomers with functionalities, and we can synthesize like a polymer. So here the polydispersity will be close to 2. So this has been done very effectively. For example, if you take like polyethylene terephthalate or nylon 6,6, all these polymers are like basically a step growth polymers. And here in conventional, as I mentioned, polyesters, amides, urethanes, all this falls under this category. But now we have like a new kind of a techniques like ADMET and all these things. So basically, this is acyclic diene metathesis polymerization, and the other one is like a copper catalyzed azide alkaline cycloaddition. Using this, we can synthesize the polymers with with a controlled fashion. For example, if you take polyethylene, if you want to incorporate like a side group at a very 10 carbon or something, we can do it very effectively using this kind of techniques. And the chain growth polymerization, whatever the polymers we were discussing, like polyethylene, polypropylene, all those polymers are basically done by chain growth polymers. Here, there are like a uncontrolled polymerization is also there, and controlled polymerization such as living polymerization, anionic, cationic, all these things are there, like radical polymerization using different kinds of techniques are there. And a lot of chemistry has been evolved in this area, and people synthesized wide varieties of multifunctional polymers such as tri-block copolymer with polymers, dendrimers, different kinds of systems has been synthesized. However, now a new system is coming that so that is like a multi-step growth synthesis. So here basically we do like a linear iterative synthesis. So we can get the dispersities in this case very close to 1. So the interested students can refer this Nature Reviews material for more details. So and also now in the area of synthesis, so we are moving from linear systems to complex materials and systems. So basically, so if you take like the basic polymer chemistry, we can obtain like a robust systems. Basically, these are thermally equilibrium systems. But when we are moving towards the different architectures, so basically block copolymers and dendrimers, if you go, so where we can have like a dynamic system is there. In this case, basically depending on the annealing conditions and depending on the kind of assembly of these macromolecules, we can have non-equilibrium structures also, basically kinetically trapped structures also. But still, we can obtain the equilibrium structures using an appropriate conditions by thermal annealing, all these things. When we are moving towards the supramolecular chemistry, those are more of dynamic in nature. So we can synthesize more and more complex systems. So maybe you must have heard Professor Subi talking on this on several occasions because he has delivered on almost all the FCBS, and mainly their group is focusing on this kind of materials. So from that, you can understand the complexity involved in these dynamic systems, organizing them in the fashion of like a block copolymers or other systems is really a challenging issue. So when it comes to the properties and function, so now it is estimated that by 2030, 10% of all the consumer products will be 3D printed. So in the case of polymers also, many polymers has been widely used for the purpose of 3D printing. Here again, like a lot of understanding is required because when we are 3D printing the systems or the products using polymeric systems, there are several factors has to be considered. For example, the rheology comes into the picture, and also the molecular mass distribution of the material is very important. Even after depending on the viscosity, you can print it into a product. Again, depending on the cooling rate and the nature of the chemical structure, you can have shrinkage in the materials, wrappage you can have. So in order to get the best product, you need to understand like how the material behaves under that conditions. Like in situ analytical techniques are required to understand the shrinkage, wrappage, all these properties. So then the polymer-based 3D printing can go to the next level. So whatever the product you imagine, basically you can print it. So particularly functional photoresist that allow sub-diffraction printing via 3D laser lithography can be envisaged. So in this case, using this 3D printing also, we can go to the structures of nanometer wide arrays of polymers for different applications, particularly electronic device fabrications. So this is also another future area which is going to emerge in the near future. So controlling the nanometer scale dimensions and generating the structures in the nanometer, a lot of understanding is required because some polymers are semi-crystalline in nature, some polymers are amorphous in nature. So you need to understand the viscosity, rheology, how they behave at a particular temperature, the flow properties, all these things has to be taken care. So other than that, we can also imagine the multi-responsive polymers, because most of the stimuli responsive polymers investigated so far are based on a particular stimuli such as light or pH or temperature or something with a specific property change. But in future, you can introduce such kind of concepts to make the materials to respond for the multiple stimuli. So that the functionality of the materials or the applications of the materials can be enlarged. The development of multi-responsive polymer systems and their translation into advanced technologies will be important aspects of the field for decades to come. So this is also very, very important. So then it comes to the sustainability, because society always demands for more sustainable solutions. There are like new technologies are required to improve the agriculture, energy generation, and the consumption, as well as access to pure water are in high demand to have like a sustainable solutions. In the case of polymers, again, we need to focus on the generation of polymeric membranes with nanoscale morphology to optimize the selective transport of ions or water. This can be used in wide varieties of applications. For example, in fuel cells, this kind of membranes can be used. Though right now we are using like a sulfonated fluoropolymers, dionomers, polybenzenols for these applications. They are not thermally stable, and we need to have like a materials with uniform morphologies. So where we can selectively transport the protons. So such kind of membranes has to be developed with very uniform morphologies. So for example, here I have shown an example of a gyroidal morphology using black copolymer system, and this kind of materials are very, very effective. And again, even in the water purification, so there are like different kinds of polymer membranes can be used. For example, electrospinning is one of the new processing techniques where you can generate the nanometer sized polymer fibers, and these can be used as a kind of a cartridge for water purification along with the other materials. So these are very, very effective. Polyacrylonitrile based fibers are widely used along with cellulose nanofibers for water purification. And there are a few companies are working in this area also. We can also use black copolymer, particularly you have to go for like a semi-crystalline kind of system. For example, if we have like a polyethylene based materials with nanoporosity, those can be used very effectively because they are mechanically robust, and you can use like a kind of a robust macroporous template as a supporting this one for the black copolymer membrane, and they can be used very effectively as nano filtration membranes. So this is an example of a black copolymer with porous morphology. And the another one is the packaging material with a stimuli responsive feature to allow the triggered depolymerization that I will discuss, and also environmentally friendly polymers for the delivery of fertilizers in agriculture. This is also a very important area which is coming up. So when it comes to the sustainability, basically we have to reuse the systems. For that, the depolymerization is one of the major area. So in the case of oxygenated plastics such as polyethylene terephthalate and polyether sulfones and different kinds of oxygenated plastics, already a lot of work has been done using like a mild hydrosilylation kind of catalyst using iridium catalyst, and we can depolymerize them into the monomers, and those can be reused. But when it comes to the other plastics like polyethylene, polypropylene, polyvinyl chloride, so this kind of depolymerization is not possible. So that's why, because when we see the global plastic uses, plastic packaging, this one, 80% of the material is coming mainly from polyethylene and polypropylene. So that's why it's the need of an hour to discover the catalyst for the depolymerization of polyethylene and polypropylene into the value-added products. Not necessarily it has to be into the monomeric state. It can be any other like a value-added product. And also we need to identify the microorganisms which are capable of depolymerization of this polyolefins to smaller molecular weight intermediates. Because in the case of polyethylene terephthalate, recently a Japanese group has discovered the microorganism where that can eat away all the polymers. So in this way also, it's the scientist has to focus to understand the different kinds of microorganisms which can depolymerize the polymers. The another challenging aspect is the biodegradable polymers, because that was never the focus of the polymer scientists in the earlier decades, but now it's in great demand because mainly we are polluting the environment with the microplastics, both soil and ocean. So in our planet, we produce around 10 to the power of 11 metric tons of biomass each year Out of this, only 3.5% of this material are used for humankind, including all food, feed, and other applications. You can imagine how much percentage of the material we are wasting. So again, it's the need of the hour to focus on synthesis of renewable monomers and degradable polymers. So this is possible, but unfortunately, cost of this material is very, very high compared to polyethylene and polypropylene. That's why they are not driving into the market. So, but new process or new chemistry is required for the generation of the monomers and polymers, and development of chemical recycling strategies are very much required. And again, I already mentioned new classes of reprocessable thermosets, where the monomers are from the regional resources has to be focused, and design of advanced catalysts are very much required for having this sustainability issues. So when it comes to the bio-based monomers and polymers, so for example, lignin or cellulose are the main sources where we can derive wide varieties of monomers, and those can be used for different applications. Even now, from lignin-based monomers, already material similar to polyethylene terephthalate has been synthesized, but still it's not gone into the market directly. When it comes to the scientific challenges here, so creating monomers from the fossil fuel is based feedstocks is about selectively introducing the functional groups such as oxidation, dehydrogenation, all these things. But when it comes to the monomers from the bio-based feedstocks, we have to selectively remove the functionality to make them like a better monomers for the polymerization purpose. So these are some of the challenges. But at present, the major focus has to be given on the cost of the material. So that is the major thing which is hindering the entry of these materials into the real market. And also when it comes to the application, so again, lots of plastics are being used in the area of agriculture. So when it comes to the fertilizer coating, you can see here controlled release or slow release of fertilizers, which is in 2018, I have shown in this bar diagram. So China is using already 46% of coated fertilizers, and Japan around 8%, US around 36%, and Europe around 10%. You see, you don't see India anywhere in this. Means we have not even entered into the coated fertilizers at all. So, but in India, because this urea is a very, very important materials, it can go into different kinds of like industries. So the agriculture-based area, which comes with a subsidy, so it should not go into those industries. So that's why our Honorable Prime Minister, he has announced that whatever the urea which is coming for agriculture should be neem oil coated. So there are like an advantage of neem oil coating, because it can, to some extent, it can reduce the sublimation of the material, and also the neem oil also it help in the crops growth. But the polymer coating, particularly using biodegradables, is a very, very upcoming area. So this has to be focused, because here we can regulate the release of nutrients from this, controlled release of nutrients. So otherwise, most in the Indian environment, it sublimes, or when it rains, it will wash out. So this is the one area a lot of focus has to be given. And the other area is like in the agriculture applications, the mulching mats. When you are traveling, you can see the usage of different kinds of mulching mats. Mainly they are based on polyethylene, and also the greenhouse covers and drip irrigation and silage applications, super absorbent polymers for water storage. There are like wide varieties of applications. In all these cases, finding a sustainable solution is one of the greater challenges. So these are all about the future applications. In last 10 minutes, I will just show the research activities of my group. So basically, we are working on different kinds of systems. Mainly, our group is interested in incompatible systems, such as block polymers or periodically spaced polymers, all those things. As these polymers are incompatible, they don't like each other. If you mix them, they macrophase separate. But if you stitch them with a covalent bond, still they try to macrophase separate. But the competition between that bond connectivity and that macrophase separation leads to wonderful morphologies as shown in this cartoon. So here you can have like a different kinds of morphologies, but this is mainly applicable for simple amorphous diblockopolymer systems. So in our case, we are interested in such kind of systems also for generating the nanoporous membranes or templates for different nanofabrication. Apart from that, we are also introducing semi-crystalline polymers into these systems. Then there will be a complexity. So there will be a competition between the crystallization and microphase separation. So our group is interested in understanding the the morphology formation using different scattering techniques. Apart from that, we are also interested in black-copolymer supramoleculars, where we are bringing both covalent bonding and non-covalent bonding together to form this black-copolymer supramoleculars. Those are the most advanced materials, and this kind of materials can find different applications. I will give one example in that area. Apart from that, our group is also very much interested in polymer nanocomposites, particularly using two-dimensional materials. So here also I will give an example. So yeah,
can you wind up, please? I was.
Yeah, sure. I will take 2 or 3 minutes.
Okay, thank you.
So we are also interested understanding the hierarchical chirality, how the molecular chirality is changing into the conformational chirality and hierarchical chirality. You can see in spherulites, you can see here. So apart from that, we are interested in polymer co-crystals, because some polymers, particularly helical polymers, have a capability of forming co-crystals with small molecules. So we can form the co-crystal, and selectively we can remove these small molecules to generate the nanoporous materials. So, and as we are in Kerala, we are also particularly the entire polymer group, we are working on different kinds of biodegradable polymers using CSIR as one of the materials. So this is one example. In this case, we have used like a black copolymer, amorphous black copolymer, where we have like a pyridine group. By exploiting this, for the first time, we have demonstrated the multi-component assembly, because in the literature only a black copolymer and a small molecule have been explored. But in our case, we have showed like a multi-component assembly using like a hydrogen bonding and also pi-pi interactions. So we could assemble like donor and acceptor molecules within this black copolymer morphologies very effectively, and we could demonstrate that the charge carrier mobilities can go even up to 1.01 into 10 to the power of -4. Later, we have done one more work by introducing the functionality for the acceptor molecule also, and those are very similar to the conducting polymers. So we also used like the new techniques. For example, the polymer crystallization so far was understood mainly using the X-ray and differential scanning calorimetry, all these things. For the first time, we have used like a vibrational circular dichroism, and we could show like for example, when we have like a poly L-lactate, which is like a helical polymer, when this is completely in amorphous, we don't see into like for example, you can take like a intra-chain interactions and inter-chain interactions. The carboxyl group, particularly that is related to the intra-chain interactions, we don't see any signal. This is because of a mesophase or an intermediate phase. We see some kind of a split type cut-in effect. Basically, if it is completely amorphous or in the mid state, that should be like a CD silent or VCD silent. When we crystallize, we can see like a split type cut-in effect. And here, this talks only about the single chain. But when it comes to the interchain, when two polymer chains are coming closer, so you can see like a COC interactions, these peaks are coming up. And the amplitude of these peaks is almost have direct correlation with the crystallinity. That's what we have shown. You can see here the VCD and X-ray and FTIR, the degree of crystallinity is whatever we have calculated with different time, which are exactly matching. And this will be like the first report in the literature. And for the first time, we are using vibrational circular dichroism for understanding the polymer crystallization process. And so we have extended this to another like a complex structures also, star polymers, in order to understand the like a core molecule behavior using both aggregation caused quenching kind of molecules and aggregation induced emission kind of molecules also. So as I already mentioned, we are working a lot on nanocomposites, particularly using synthetic clays and also like a different kind of zirconium phosphate based layered materials, boron nitride based layered materials, all these things. Apart from that, as a group activity, recently we have like a very good success because of the ban of single-use plastics. The many industries are coming forward for alternate solutions, and we are working very actively in this area to make different kinds of cutleries and other materials. Even we have developed a technology for making completely biodegradable mulching mats, acoustic panels, all these things using coconut coir and polymer composite materials. And this is my group, and thank you very much for your kind attention. Yeah.
Thank you, Bojay, for a very like a clear presentation on polymers. What are the challenges and what is the future in this field? So the talk is open for questions. We can have probably 1 or 2 quick questions as we are running late. So the participants can write the chat box if you have questions.
Subi, I don't see any questions, so let me ask one question to Boje. Subi, can you hear?
Joshi.
Yeah, go ahead.
Yeah.
Boje, you know this with this pandemic, most of the shops are using this gloves and other things, which is probably going to be a big problem in disposing of them, because every day every shop is giving gloves to the people who are entering the shop.
Right.
I mean, that is just an example. So this we were trying to eliminate this single-use plastic, but now there will be a big surge. So what in your opinion will be a sustainable way for us to go forward? I mean, provided if we have to live with the single-use plastic.
The recycling is the only option. Basically, single-use plastic, particularly the labelings, this kind of applications, we have to take an extra care. So, because cleaning those materials are very, very important. After that, that can go directly for the recycling purpose, because we're using it only for a single use. And if we can identify it and it can be sent to recycling, so that is the only option as of now. So, because those are not very high quality materials, so you can't make high quality products out of it. Again, you can use for such kind of applications only. Only recycling is the option.
Yeah, I agree, Boje. That's probably one of the biggest challenge polymer chemistry for future is the recyclable polymers, because circular economy, and I think that's going to be an important challenge for all of us.
Yes.
Okay, so if no more questions, I will stop here because considering time. Let us thank Dr. Boje Gowde once again for a wonderful talk. Thank you, Boje.
Yeah, thank you, Subi. Yeah.
So let's move to the next talk. This is going to be given by Dr. Sarit Agasti. Sarit, are you around? Sarit?
Yes.
Yeah. So Sarit is a kind of, he's a new face to the FCBS community, because this is the first time he's going to deliver the talk in the FCBS platform. So he's my colleague at New Chemistry Unit of JNCASR. He works at the interfaces of chemistry with biology and materials. So he's probably, when he joined our institute, probably, he has a lot of expertise in super resolution fluorescence microscopy. So I think when he joined our department, probably is one of the first one to set up such wonderful equipments in the department. So he has, within last 5 to 6 years, he has made a lot of interesting contributions, and he collaborates extensively with many material chemists and so on. So he's a very active, dynamic young chemist, and he's already recognized with many awards. So this year he is selected as the Young Associate of Indian Academy of Science. And most importantly, he's a Wellcome Trust intermediate recipient. And also he is chosen by the James Journal of Material Chemistry as the young emerging investigator very recently. He works on various fields. As I mentioned, super-resolution microscopy is one of the things. And then he also does a lot of supramolecular chemistry, host gas chemistry, and so on. So Sarit, with this brief introduction, you can go ahead with the discussion.
Thank you. Am I audible properly?
Yeah, we can see your slides as well. Yeah, can you make it?
Is that fine? Is it full screen?
Yeah, perfect.
Yeah. Yes.
Okay, good. Thank you. I must thank Subi for nice introduction, as well as I think I must thank the other organizers for hosting this, and also inviting me for the first time. And which I'm very excited to talk about some of the things which we pursue in the lab, as well as something which connects to many aspects with the life. For example, what you can see here is actually a sample which is being imaged utilizing the power of chemistry. Like, you can see here the things which glows very nicely. And you can see there are a couple of different colors, and obviously these are coming from oil-sweeted molecules, which is called fluorophores. But what you can see here, these two things, you can see one which is kind of an yellow color, and which is kind of in a blue color. And to be very specific in this case, what we are looking at some cancer tissue sample from a real patient sample. And the thing what you see as yellow color is actually the diagnostic marker of a diagnosis of the cancer. So as you can see here, this provides you with a very basic understanding that importance which it plays if you are able to see things which is inherent to life, right? So it can be used for diagnosis of many diseases as well as many fundamental aspects. So let me just tell you with a very general starting point. So the basic of all this, what I have just shown in one slide, is comes from this idea of fluorescence spectroscopy. I think all of you would probably be aware, where a molecule, when is excited, and it will emit a fluorescence, and you would be able to record the emission using a simple spectrophlorometer. Right. So I think almost all of us has at some point of time used this kind of instrument to record the spectra of a fluorophore in a general settings. But what provides the more benefit, or the next step above, which is called the imaging, is actually not only you will be able to understand the fluorescence or fluorophore, you should be able to understand where it localizes. Right, so that's called the imaging, like taking a photograph. So here are a couple of examples. As you can see here, is that some of these fluorophores are now integrated into the biological systems, right? And also a very example, which is let me just take the. So these are the examples. What you can see here is that the fluorophore is now integrated into a biological molecule, which is a jellyfish. And here what you can see, it's integrated into a mice. So that's why it's glowing. And you can clearly see the kind of position or the kind of spatial informations which it can provide. And also very interestingly, what you see here, this is actually a material sample prepared by Professor Subi George, who just spoke a little bit before. And you can see that these are the molecules, again, a very, very important molecule, which is called block copolymers based on a supramolecular chemistry. And again, you see that these has a very different kind of arrangement. And these are made out of two different monomers, right? So that's why you can see a block pattern. And also you can see that you can not only give the position, you can give a color, and that color also determines what molecule you are actually looking at, and also their spatial distribution. So here what you can see here, that it is a cell, and this is a nucleus, and both are actually stained by two different colors, cell membrane and nucleus, which is again providing you then information about the general applicability of the fluorescence imaging. And as you can see, all of these are, or subset of these, are actually looking at how the life behaves, forms, patterns, many things. And also here what you see is actually an examples of the neurons and how it is distributed in the brain, right? As you can see that their patterns are completely different what you will be seeing in other places, right? So this pattern of the molecules or informations are integral to the form of life. And that's why you really need to understand and image molecules or life in vivo, in cells. So that's why the fluorescence microscopy has been one of the most important in these aspects. And as the behind to all these molecules are actually this a beautiful set of dyes. Okay, so there are two types of fluorophores generally people would be using. One is called the fluorophores, which are based on the fluorescent proteins, and the other subset is based on the small molecule. But as a chemist, I think this is what excites us a tremendous amount, that these molecules are synthetically made, right? And you have enormous opportunity to tune their property, right? For example, think about the brightness, right? Think about how stable they are, like, photostable. What about their wavelength, right? So there are many parameters which you can very specifically tune with enormous possibility, which provides a greatest new tool of chemistry to do a biological imaging in these settings, right? So these are some of the examples what you can see here, that you can produce molecules which can emit fluorescence starting from 400 nanometer to all the way to like 750 nanometer or so, and they're actually very, very bright, and they're actually highly photostable. So these are the examples or the chemists which they can do. And as you can see that almost all the molecules are highly conjugated systems. So these are the basic properties which you need to deal with when you are making a fluorophores. And not only for the biology, I think people who are also interested in looking at molecules in the materials, for example, catalysis like photocatalysis or any sort of nanomaterial based catalysis, they also look at fluorophores. For example, in this example, what you see here, this molecule, which is actually not fluorescence, can turn to fluorescence based on this catalytic property of this nanomaterial. So that by measuring the fluorescence, you should be able to understand that these molecules are behaving like this way and their catalytic properties. So this has more application in these two, but I'm going to talk about more onto the biological aspects or life materials or life materials aspects. So now here, what you see here is an example of a microscope which can be used to encode or understand the spatial information of a fluorophore. So it's a very simple design. There is no complexity in here. So it is a little bit upgraded version of a simple fluorimeter. Only thing what you have here, you actually have a sample stage, right? Where you are actually going to place your sample, and then you are going to move your beam or beam of light to record the spectra, right? Whereas in a fluorimeter, you don't move the beam because your sample, you don't need the spatial information. But here, what you are going to do is that you are going to provide a stage where you are going to place your sample, and that sample is going to be moved around. Whether you can keep your beam at the same position, or you can move your beam also, keeping the position same. So both of these will provide you an information, both X, Y, or many times also Z, right? So that is the spatial information what you are going to get. So now this is in a complex form what commercially available microscope will look like. And also this also integrates all the parts what I have shown you before, but with a little bit more, casing. For example, you need to have excitation light source. You need to, have a camera to detect it. And see, this is kind of excitation light source, and this is kind of a camera system which you kind of detect the light from there, and also you can detect it by your eyes also. So, but this is just an example. And there are kind of two types of microscope which is generally people would be using in standard laboratories. So there are two which is called the simple epifluorescence or wide field fluorescence microscopy. And the second thing which is very, very important is called the confocal microscopy. So this is called confocal microscope, and this is called the wide field fluorescence microscope. So what is the difference between these two is that you essentially utilizes a very wide area of illumination, as you can see the samples, and then that is recorded in your sample. Whereas for the confocal system, you will actually illuminating a very smaller area, and also you have abilities to record information from the Z depth. Okay, so you not only XY, you will be able to record in the Z depth as well. So this is again, you can see the difference where in a simple system, which is a wide field setup, you will be able to record a small area, but wide field, where is a confocal system, you should be able to record in the focal plane. Anyway, and this is something which is a home built setup. And as you can see here, this also integrates all the parts which I have shown you before, but in a real scenarios or in a lab, right? So what it combines here in the few things, as you can see here, you have couple of light, and lights usually are exciting the molecules, and that light could be either a simple light source like a halogen lamp, or it can be something a little bit more upgraded or complex version of it like lasers, right? So these are high power lasers, and you can combine them together. You can see there are 4 different kind of lasers you can combine, and you can combine together, and you can beam it, and you can project it into your microscope, right? So this is where what I was telling about the stage, right? So this is where you keep your sample, and you can see that all the excitation lights comes here and excite these molecules over here, right? So this is the stage what you are going to see. And then, behind this setup, this is actually which is powering up these lasers. Behind this is actually there are camera, right? And then once these molecules are excited, the emission light is now detected by the camera, right? Which is actually hidden behind this setup, or you can detect it in an eyepiece, which is you can see it by your eyes as well, right? So once you record this, you should be able to see how the spatial information and how the fluorescence of a sample looks like. Okay, so this is what I really like about this fluorescence spectroscopy, and this is a recorded image which is recorded in our lab. And as you can clearly see is right hand side, right, which is an fluorescence microscope image of a cell, and the left hand side, and it's a comparison between a TEM image, which is a transmission electron microscopy image, which is usually used it for molecules, like for example nanoparticles in other small nanomaterial system, to understand their size and various other properties. So now the distinct difference between these two you can really realize is that when you are recording these molecules in the TEM, you see they are black and white, right? Whereas because the fluorophores as a color-coded information, right? Because the fluorescence you can really distinguish based on what kind of wavelength these fluorophore molecules emit, right? So based on that, you can assign them a color, and that gives you information about many different components in the cell. Okay, so like here, like what you see in this right-hand side, there are at least 4 different kinds of molecules with a very different structural organizations are present, right? And which are actually information which is providing you that how the molecules are distributed in a human cell. Whereas in the left hand side, you only see that there are 2 things, something white and something black, right? So that's why the fluorescence is much useful in here to know more about a biological system, right? And another important thing what you can see here is that if I play this, what you will see that not only you can know the information, you can know about the dynamics, right? The systems are alive, right? So that's why what you see here is a fiber which is called a microtubule, which is an integrated part of a human cell, and how they move, distribute in a real time, right? So these samples what we are looking at is actually live sample. And now as the fluorescence or fluorescence based imaging technologies provides you no detrimental effect to the cells, right? The cells are, that's why, alive, right? So that's the benefit of utilizing fluorescence microscopy to investigate or to probe or to image or record a biological sample or a living sample. Whereas if you think about the TEM, you know, that's a very high power electrons you are using, and that's going to distract, right? That's going to kill all of your samples. This also applies for many of the soft materials, right? Where the electrons can really kill all of your samples, and it can, you know, really destroy your samples. So that's a good thing about fluorescence microscopy. So far I have told you that all are good about fluorescence microscopy, but there is a very big challenge. What you can see here very clearly is that you can essentially look at the samples here. Each of the nanoparticles, what you are seeing here is around 5 nanometer of size, or 5 to 10 nanometer of size. Whereas the resolution what you are getting from the fluorescence microscopy, what is shown here, is extremely low. You are only able to see molecules which are around 200 to 300 nanometer of size, right? So as you see here, this is extremely difficult to probe molecules at their actual resolution using fluorescence microscope. So let me define you what I mean here. So this is what is called the resolution of an optical microscope. So although we would like to use fluorescence microscope or optical microscope for investigating life or biology, but the challenge comes here that you are not able to resolve molecule beyond a certain limit, which is really possible by methods like TEM or ASM, right? Like here, as you can see that I am able to see an ant, which is around 1 millimeter of size, by utilizing my eyes. You can see here by your eyes. If you go to little bit small like mammalian cells, you can see a simple microscope. If you want to see a bacterium or a cell organelle, then you can look at a little bit complex microscope, which I have shown you so far. But Once it goes beyond a limit, which is called the Abbe's diffraction limit, which is around 200 nanometer or so, then you are not able to see molecules or not able to resolve those molecules. But there are many things lies in that region. For example, a virus, now it is probably everybody would be aware of the virus and which kind of detrimental effect it makes to the human life. You can't see them by using optical microscope. You can't probe how the virus would be attacking a human cells and how they are distributed over the cells, right? Because you cannot resolve by optical microscopy, although optical microscopy is ideally suited for that. You can see a protein molecules, which are the fundamental building blocks or functional component of cells or human life. This is again a resolution of 10 nanometer or so. Again, if you want to go beyond that, small molecules which are again much low. So there remains a really huge gap in this case, that we can't probe our molecules beyond a certain limit. So now I'm not going to details on this, but you might think that you can keep on magnifying things and you can resolve any molecules of any size. But actually, it's not the case, because after a certain point of time or certain limit, you are going to essentially bound by the resolution due to the diffraction. For example, the light diffracts, and the spot which is supposed to be look like this is going to get bigger because there will be a diffraction of the light you are going to see like this. And that's what, like if a light is emitted from a single fluorophore, single molecule is emitting light, although they are supposed to be 1 nanometer, but after it comes to a recording sample, you are going to see it's much bigger, and the point is going to look like this, right? So this is a single molecule emitting light, and that is what recorded on a camera. And as you can see, this is much bigger, and usually this is around 200 nanometer of the size. And the resolution will be defined again if two molecules are separable by more than they are distinguishable. That will be the resolution. And now you can clearly see it's around 200 nanometer distance between two single molecules. They are separable, but when they come close together, they are not separable, right? That's why they merge together and shows you a single spot, right? Although they are two different molecules. And this is again defined by this Abbe's resolution, which is lambda by 2 Na numerical aperture. In best case scenario, it is around 200 nanometer of size. Okay. So again, going back to the same kind of and a little bit more elaborate what I mean by resolution. If you have two molecules separated by more than 200 nanometer, you are able to resolve. But if they come close together, and then these two Gaussian is going to fit, right? So and then they are going to show us same spot. But essentially, what we can do, this is a kind of microscopy what is used regularly in our lab, which is called structure illumination microscopy, where you can utilize a pattern beam, because pattern beam will be overlapping with your sample, which is a higher order information, right? So those higher order information can be used by overlapping with a pattern beam by extracting the informations which will be higher order information, right? So those kind of in microscopy would be called structured illumination microscopy, because you will use a structured illumination beam to resolve the molecules beyond the diffraction limit. So that's what you see here, a wide field image, which is a standard microscopy like this, and structured microscopy illumination will be showing light. So similar thing, as you can see here, this is recorded in our lab, and as you can see in the lower side, this is a standard diffraction limited imaging, which is a resolution of 200 nanometer. But if you apply this sort of a structured illumination setup, you will be able to very clearly image and resolve the molecules. So the resolution of these molecules would be around 120 or 100 nanometers. So around two-fold increase in resolution. So again, as I told that by utilizing this, you can record live samples. So now we are recording an image which is double the resolution which you will be getting with the other methods or standard microscopy. But now here you will be able to resolve molecules better, but able to resolve molecules and image when they are dynamic and moving. And this is another image which will show you the real power of this sort of a super resolution microscopy. And as you can see, this is a cell which is now moving, and you can clearly see that how cells are expanding and contracting, and they're moving very, very different places over the time, right? Now you can see it very clearly, and these images are 20 hours images are combined, right? So now, hello, am I audible?
Yes, go ahead.
Hello. So I'm fine now. So I saw some message that my connection is not stable, but it's okay, right? Okay. So yeah, so this also shows really the power of microscopy, what you can use, and you can see the molecules when they are moving and they are forming new networks. They are essentially showing you that how the form of life is, and we are imaging it beyond the resolution which we can use using a standard optical microscope. So again, I wanted to show you really that this is the power of microscope, which you can expand to many other fields, like, you know, Subi works on a soft materials called supramolecular materials, and he is very interested in looking at how these molecules self-assembles, form different sort of structures, form different sort of blocks, and this is some of the samples from his lab, and you can clearly visualize how these molecules organizes in a kind of block structure, right? So this is also have some sort of spectral information which gives you color, and as well as resolution which gives you the distinct between these two color domains, right? Which is going to be very, very useful in many aspects. But as I told that, you know, the improvement in the resolution is around 120 nanometers, or 2x improvement, and you get 120 nanometers. But essentially, as I told that we would like to go much, much more, and we would like to see molecules probably 10 times more resolved, right? For example, 10 to 20 nanometer would probably be something which you would like to aim for if you really want to resolve a single protein or single protein complexes, or, you know, one molecule. So this is the strategy 2, which has been tremendously useful, and this is a strategy developed by mostly dominated by the use of physicists, because they are able to utilize various sort of strategies, like utilizing a beam pattern, which is very, very different than what would be used by standard microscopy. What pattern, and also utilizing this technique which is called stimulated emission and depletion. So this is a technique where you can essentially deplete or eliminate fluorescence from a given molecule by providing it with a high intensity laser beam, which is slightly shifted to a red wavelength. Okay, so this is a kind of concept called a stimulated emission and depletion. So now, as you know, that if this is the fluorescent beam I am using for imaging, so the fluorophore is going to emit from all the places. But if I am able to do like this, so I have an excitation source which looks like this. So I'm going to get, this is, let's say, 200 nanometer of beam, but I'm going to generate a state beam pattern. Means any molecule within this beam is not going to have any fluorescence emission, because they are emitted by using this stimulated emission, right? So no emission from this sort of a beam pattern. So now if you overlap these two, so effectively what happened, you are not getting emission from the state pattern beam, you are only then able to get emissions from the overlap of these two beams. Now once you overlap these two beams, you are effectively collecting the fluorescence only from the very small space, small region. And that gives you a much improved resolution, and you can get an optical resolution of 30 to 50 nanometer. But now it's also been able to improve much, much higher, right? Utilizing this sort of an state beam pattern. So now the third strategy, which I think the most contribution has come from the use of knowledge on chemistry in this aspect, called the single molecule localization. So what do we mean by single molecule localization? So for that, I'm just going to tell you a simple idea what we can utilize, which is called if there is one molecule in your field of view, right? You have only one molecule you are imaging. Then what you are going to get is this sort of an image, right? As I showed you before. And if I fit this single molecule into a Gaussian beam or Gaussian fitting, the center of this Gaussian fit is going to tell you what is the exact localization of this molecule. Okay, please see it carefully, that what you see here, you have a exact beam, and that beam is going to tell you the exact localization of the molecule, right, by fitting it into a Gaussian. So this is good if you have only one fluorescence emitter, only one molecule fluorescence emitter. But if you have two fluorescence emitters, as I have shown before, that are less than 200 nanometers, then this below scenario happens. You cannot fit it into two Gaussian, right? That's why you are not able to resolve. Now, what if I am able to do this trick? The trick is called the fluorescent blinking plus single molecule localization. Fluorescent blinking means this. So now this is a image where this is a molecule. There are a dense cluster of molecules packed together in a diffraction limited spot. For example, the total size of these molecules are around 200 nanometers. But there are many molecules. So now if all of them are emitting fluorescence together, then essentially this is what you are going to get, which will be called as a diffraction limited image. But if I have the ability to do this, like let's say I have the ability to turn off all the molecules in this field of view, but have only one molecule providing the fluorescence, right? So if I have only one molecule, all others in off state, then I'm going to see only one spot, and I should be able to fit it by utilizing this sort of Gaussian fitting. I would be able to give it a spatial coordinate which is close to nanometer resolution, right? I can precisely define its coordinate. So once I have done that, I can essentially turn off this molecule and turn on a second molecule in this field of, right? So if I do that, then now see that other molecule is off, only one molecule is on. So I can again fit it into a Gaussian and provide it with a spatial coordinate, which is a nanometer resolution, right? And I can do this over a period of time for different molecules, and I can combine all together, and you can provide it a combined map, which will be resolution wise. Each point is nanometer precision, right? Is that clear, right? You can see it again, that I have this sort of scenario when all the molecules are emitting fluorescence. I can't fit all of them in a Gaussian and get a precise location. So I do a trick. I turn off all the molecule except one or a few in this field of view, and which is exactly separated from all others. I fit it in a Gaussian, provide it a specific coordinates, which is nanometer precision. I do this over and over again for many molecules, and finally I map them together and get an image which is exactly a nanometer precision, right? So these tricks, if you apply, then you should be able to resolve or get an image of a molecule which will be providing you with a resolution which is much better as compared to any other strategy. And how do you do this sort of a trick? So that's why the dye or the property of the chemist or chemical tunability of the molecule comes into play. And as you can see here, if you take a dye, for example, a cyanine dye, and if you provide it with a reagent, which is, for example, a thiol, and if you irradiate this molecule using light, this molecule will go to something called a dark state, right? Because this thiol will react with this conjugated molecule and break the conjugation, right? So this molecule will essentially be something in the dark state, like not emitting fluorescence. But the beauty of this molecule is that you can shine another wavelength of light. Let's say you can shine a UV light into this, and that will bring back into the fluorescent state. And this can be cycled back between the dark state and the light state, right? By cycling back between fluorescence on and off, you can essentially select only few molecules to be in the photoactivated state and some molecule in the dark state, right? So that's why you control the amount of molecule which you can actually see in your field of view by resolving them in a sparse distance, right? So this is a chemical trick which has been extremely useful, and this has been applied to resolve molecules in very useful manner. And as you can see here, you can resolve the molecules like, this is a diffraction limited image, and this is what you can resolve utilizing this technique. And because of the tremendously useful nature of this strategy, this the super resolution imaging techniques has been awarded Nobel Prize in 2014 for the tremendous contribution of these 3 people. So the first people, I will start with the people, this Moener, who is first time observed a single molecule under the microscope. Then the middle person, who is the Stephen Hale, who works on the state techniques, and the Eric Bedrick, who actually provided insights about biological imaging using single molecule techniques, like specifically the photoactivation, which I have described, right? So these 3 has been a tremendously contributed to that field and build up a strategy which is called a super resolution imaging technique. So, Subi, how long should I have more?
So you can take another 10 to 15 minutes.
10 to 15 minutes. Okay, thank you. So what's next, right? So this is what 2014 happened. Then what's next? What are the challenges actually remaining, right, in this field of super resolution imaging, and where the field is going, and what is for research? I would like to give you an idea. So if you think about the desire or the importance or what people would like to get from an optical imaging can be divided into these 4 coordinates. Okay, so one is obviously you want to resolve molecules, right, resolution, right, as we discussed, and that has been achieved with a strategy which you described. Then you would like to record, right? Resolve record means over time you want to record it, right? So that's also important. You want to differentiate, right? You want to look at molecules, large number of molecules, resolve, and as well as you want to differentiate between 2 molecules, but not only 2, as the life depends on many number of molecules, probably hundreds, thousands. You would like to differentiate between as many number of molecules as possible. And also the last thing, also important, quantification, right? You would like to quantify how many number of molecules is present in a given scenario, right? For example, any event in the living context would require a certain amount of molecular concentration or cluster to provide an effect. So that's why quantification is important. But the challenge is that all the strategies so far does not able to provide all of them simultaneously in a single setup. So that's why there are many unresolved questions or improvement are necessary in all these different directions to provide necessary tools or techniques, strategies for a chemist or a biologist to interrogate many systems. So for example, I think the combination of chemistry, physics, and chemical biology is going to be a forefront to resolve all these different parameters and combine as many of them possible. For example, one limited things which I can describe here is called limited multiplexing. Multiplexing means how many number of fluorophores or how many numbers of molecules you can investigate. So as you know, the fluorescence spectra of a given molecules are very broad, right? Because they are broad, there is going to be an overlap between if you are choosing more than a certain number of fluorophores, right? So usually if the number of fluorophores are 4 or less, you can resolve them well separated spectra, right? Because as we are looking at a visible spectrum range between 400 to 800, you can possibly fit 4 fluorophores which can be distinguished. But if you want to look at more than 4, that's quite impossible by using standard fluorescence microscope. So that has to be generated. Then many of the strategies for switching the fluorophore between on and off states, as I told, requires this specific buffers. For example, agents which are toxic to the cells, right? So that's why you probably want to use a strategy which can spontaneously provide a molecule into a blinking environment without utilizing a photoactivation, without utilizing something like thiol-based reagent. Also, many times, many contexts for standard laboratory, you would like to get an instrument which is much less expensive, right? So all these are kind of things which people need to work on and develop things. For example, I would like to show you in this case that when you use a setup like state microscope, you can see here that you can see the live things, but you see what happens over time. You essentially breach the molecules within few minutes or few seconds, right? As you can see here, although you are able to resolve, but the demand of the state microscope is high power laser, which kills the fluorophores very quickly, right? So that's why the fluorophores are eliminated. Another thing also I'm going to show you. See, this is again under the state microscope, and this is what we are looking at is a mitochondria. And what happens you see over time. See, the mitochondrial morphologies are changing. You see they are stretch, well behaved, right? But slowly they are becoming spherical, right? As you can see clearly, and that actually indicates the mitochondria are becoming unstable because the reactive oxygen species are generating in the system, right? Because as you are using a property of the molecules, you are using exciting the molecules in the cells, and they are generating a lot of toxic species, right? So that's what happens when you are thinking about utilizing high power laser, right? You can see here. So phototoxicity under high intensity stained illumination. So now I'm going to give you a hint that how we are thinking about contributing in this direction by utilizing a strategy which is called autonomous blinking. Autonomous blinking means, as I have shown you before, that the blinking is introduced by a means of chemical means or using a light induced activation. But here, what I'm going to show you that here, you really don't need to induce blinking by any other external means. You can integrate this in your molecule such as that they can blink autonomously. Like, for example, here we are using something called a host-guest chemistry. So this is a simple system which utilizes something like an molecular association and dissociation. This is inherent to, I think all of you would be knowing something called an dynamic equilibrium. Once you mix these two molecules which interacts under a non-covalent interactions, and if they are binding together, there will be complex formations and they will be under equilibrium. So now if they are under equilibrium, you can think about they are always, forming a complex, they are dissociating. So they are always moving into right hand side and left hand side. What we thought, why don't we utilize this sort of a concept and integrate into a fluorescence microscope? So what essentially we can see here that if the complex is formed and if are able to show the complex formation under microscope, and this could be something called a binding event emitting a light. An unbinding event is going to show no light, right? Something like this. When they are bound, you are going to see a light on state. When they are not bound, they are going to not show a light, right? So here you see I am able to generate two states, on state and off state, but not utilizing anything which is related to external application of light or any reagent. I am only relying on the inherent property of these molecules to dynamically assemble and disassemble. Does it work? As you can see here, one example that once I put these molecules under the microscope, they are going to provide you with a blinking pattern, right? You can see the molecule comes into a field of view called a blinking spots, and they disappear, and this continues over and over. And here I am just imaging, not utilizing any sort of external factor to induce blinking. So this is an autonomous blinking nature of the molecule. Now, if I combine this together and form a super resolved image from the cell, this is what it looks like, right? So this is what a standard microscope image. And if I overlap the strategy, what I have just showed you, this is what you see. Now you see that you are able to see molecules with much clarity and with a resolution which is below 20 nanometer of resolution. Now you see that utilizing the concept of dynamic equilibrium between two molecules, you are able to bring a microscopy technique where you are able to resolve molecules in the cells in the living system with a resolution below 20 nanometer, right? So that's a tremendous importance, that how you can use chemistry to connect to the life to resolve molecules there. So now the last part that I'm going to talk to you, that how to increase the number of multiplexing, how you can resolve more than 1, more than 4, more than 10 number of molecules in cells. So here we have utilized something called the dynamic equilibrium between DNA, right? As you can see, the host-guest interactions are similar to the equilibrium can be established by DNA-DNA interactions. So that's what we did. We made some DNA structures. We put these DNA molecules into the structures, And I think we have an expert here, Reggie, who knows about this sort of a DNA structure very well. He works tremendously in this field, contributed in many aspects. So you would be seeing this, that this can be used also a probe for imaging, right? DNA structures. And when you image using these DNA-based strategies, you can clearly see these molecules are distinguished very clearly. And if I zoom in, you can clearly see the molecules which are separated by 20 nanometers are clearly visible, right? As you can see here, this is a grid pattern. Each molecules are distinguished very clearly. But the beauty of this strategy, so we have also done many other images, like this is a kind of DNA nanorod, which also we have imaged by integrating many other small molecules into the structures. Many things we have done. But the real importance is that this strategy can provide infinite multiplexing strategy. So you can image large number of molecules, because the beauty of DNA is that you can create a DNA strand of orthogonal nature or a unique DNA sequence for n number of molecules, right? Because you know the DNA sequence you can control very clearly, and you can create a DNA sequence which are very unique. So that gives you unique identification to each molecule. And if I am able to read out this each unique identification, then I should be able to assign them with a color, and I should be able to resolve that. So that's what we have done here. And you can clearly see that within a cell, I'm able to image many different kind of molecules, providing many different structural organizations. And once you put them together, then clearly see they provide you the clear and complete picture of many different molecules in the cell. And you can do this also in a in neurons. You can do it. So these are the neurons connected together. You can even look at different molecules in neurons. So this is another important thing to think about, that the structures which are formed in the cells are very periodic. For example, this is a pattern which are seeing in the neuron of the axons. So these are the molecules which are arranged in exactly, you see, 200 nanometer periodic pattern. You can clearly see it over here. Again, you can do 3D information in this. For example, over here, you can look at here, for example, 3D information in this sort of a cell, right? You can look at all different dimensions. And with this, I would like to conclude here, and I would like to acknowledge a couple of people, specifically Professor C.N.R. Rao, who has been tremendously instrumental in setting up all of this. Also, thanks to my group, who has been tremendously useful, and a couple of collaborators like here. And as well as I would like to thank I think our department support from here, and also specifically like to thank Professor Subi George, I think, who is in the audience, with whom we tremendously been collaborating in many aspects, and has been tremendously useful to really set up this state-of-the-art facilities. And also I'd like to thank various funding agencies for their tremendous support. And I will be more than happy to address any questions which you might have. Thank you.
Thank you, Sarit, for a very clear introduction to the super resolution fluorescence microscopy. A lot of beautiful images.
Thank you, Subi.
The session is open for questions. I don't see any questions in the chat box, but anyone can.
Chat box, any question there?
No, it's not there in chat box.
Okay.
Reggie has a question.
No. I'm fine. I am about to tell that students may email Sarit if they have any question in the future.
Sure. That's also definitely a great idea.
Yeah, Sarit, just for a continuation of your presentation, I think at some point of time we discussed also. With one of the limitations which I see when you want to go to high resolution using the super resolution optical imaging is, if you want to go to the kind of real high resolution, you need to modify your system. Okay. So from a materials point of view, I mean, when we work on systems, and that's a big limitation to us. Like, you modify the system with an additional probe, which can change many things in the system. So is there any solution? What you
see, the thing is that there's no deniability in this fact that if you want to resolve, you can't achieve all these parameters together. If you really want to resolve high, so number of photons you need to collect has to be higher. I think that if that is lower, it's very difficult. So that's why I think the fluorophores which are traditionally used, I think that's are going to perturb your systems. I think that is definitely a challenge. And I don't think that I have a very clear solution, or I don't know if anyone has. But one thing I can say that what I'm seeing is slowly that people are investing a lot of effort or synthetic effort to make smaller molecules, smaller fluorophores, with properties may not be competing with the best fluorophore, but decent, but much smaller structures with the fluorophore fluorescence property which are okay, good. So those are kind of development I think which is happening in the field. So I think as we proceed, maybe we should be able to come up with smaller fluorophores with suitable property. And the second thing which is also happening, which I think could be useful, is that I think not to modify the system, but something like intercalating dyes. So I think many times molecules can be intercalated in those sort of a soft structure after you form your molecules or polymers or whatever you form. And there is also a tremendous improvement there to make molecules which are specifically fluorescent when they are intercalated. And those are the probes I think has abilities to tremendously help. And many times they don't have to intercalate also. So many times what happens, just a surface association can provide a suitable environment for a molecule to be highly fluorescent. So there are new sort of dyes which actually looks at polar versus non-polar environment. So when they are in a non-polar environment, they are not fluorescent, but just a change in polarity on the surface of the polymers is good enough to provide you the imaging capability. I think that is the way we can solve some of the problem in this area. But as you told correctly that there are, I don't know other means. Is it make sense?
Yeah, it definitely makes sense. And,
but this, I'm very excited about this sort of a polar molecule. I think we also have started using a couple of them. If you think that something could be useful, we can connect readily there to polar surfaces will provide you a tremendously improvement, like, almost like 1,000-fold improvement could be possible in many instances.
Yeah, so something which is another general question is, so you showed some pictures on the live cell imaging.
Right.
So we know that most of the time we do it not in vitro, like outside these cells. So what are the challenges when you try to do a kind of microscopy in a live cell imaging?
Okay, that's a very good question. I think the biggest challenge in this case, I would say that how to level a specific molecules in the cells, which gets to a very challenging aspect. Because see, you would like to use a synthetic fluorophore because those are highly photostable and they are small, but you need to find a suitable way to target this molecule to a specific organelles or specific molecules, right? So now the targeting becomes challenging because most of the time the targeting happens utilizing antibodies, which I think almost all of you would be knowing that specifically bind to a molecule, but antibodies are too big and they can't go inside the cell, right? So that's why the strategy has to be developed. The small molecule has to be found, which specifically goes and bound to a specific molecules inside the cells, right? So that's one of the challenge, which is the labeling technique. How do you label a molecule? So that's why there are strategies. For example, we are using many small molecules to target a specific, assemblies in the cells. For example, we use microtubule binding drugs to target microtubules. There are good things for mitochondria also. I think Reggie also would be knowing very much. I have seen a couple of his paper. He used mitochondria targeting molecules, which can go and specifically bind to mitochondria. But specific challenges exist because none of these things are standardized for all the other molecules. So there has to be an improvement in there. And the second thing I think is that the cell permeability. So that's something which comes to a big problem in many cases. Because if the molecule or dye you synthesized, it is not cell permeable, then you are not going to get anything, right? So in that case, you need to design a probe such a way that it can go inside the cell and freely diffuse inside, because cell membrane is one of the biggest obstacle for any live cell imaging. And the third most important is that what we are also working in many aspects, that fluorophores which we are using, it has to be removed from the system before you actually go for imaging. Excess fluorophore which are not bound to your target has to be removed, right? And many times, suppose you want to image something in mice, in a human body, there you cannot remove the excess fluorophore, right? So how to tackle that? So the one way to do that, as I was discussing, that you generate a probe which is only fluorescent when it is attached to the target, right? So that way you don't need to remove the excess fluorophore. Any non-specifically bound fluorophores are not going to be fluorescent, right? So this sort of conditional fluorophore or fluorogenic probes are going to be the next generation of probe which people should think of. So that's what I will lay down three. One is, first is kind of a labeling strategies. Second is molecules with the cell permeability. And third, fluorophores with a fluorogenic property or a labeling technique which will provide a fluorogenic property. So these three has to be tackled for a better imaging in live condition.
Thank you, sir. That was very clear.
Subi, can I have one?
Yeah, Reggie.
Can I have? Yeah, okay. Sorry, the excellent presentation, very useful and informative. So I have a question, rather a curiosity to know. So you said when you have an ensemble of fluorophore, you said in order to improve the resolution, you will be selectively excite one molecule, and you will other molecule will not be will not be getting excited. How do you technically do that?
So the thing is that this process, although I have shown a simple form that I am selecting a specific molecule to be in on and specifically others to off, but it does not, it's not like exactly like this. It's a stochastic process. So I don't control each of the molecule, but I control the number of molecule on the on state. So let's say if there are 100 of molecule, I can give a trigger, right? For example, let's say I have 100 molecule, and if I put only 5 fluorescent molecule, right? So only 5 molecules are going to be bound, and they are going to be specially distributed.
I see.
Right. Okay. So I just only control the number of molecule in given frame. I let it be stochastic so that at least I don't see them and together.
I see. Okay.
Does that make sense? Yeah.
Yeah.
So because in a standard fluorophore, what you do that all the fluorophores are at a time, all are attached. And that's why when you use dynamic equilibrium, only few molecules are attached, other molecules are not attached. Next dynamic equilibrium, other molecules will get attached, those molecules dissociate. So this is a stochastic process which can be controlled.
Thank you, sir.
And actually the other what you were telling about the specifically how do I turn it off and on. So that is done in state. If you think about the state microscopy, that is the concept. You only excite or get emission from only few fluorophores which are within that 5 to 10 nanometer radius. And other molecules in the other parts, you make them off by the state beam. So although they are not projected that way, but I think this is a targeted emission from a very specific spot.
Let's stop the discussion here. And Sarit, it was a wonderful presentation. It's nice to see that from confocal, like a 300 nanometer resolution to you can reach up to like a 50 nanometers. It's amazing. So very nice, and thank you for introducing us to this field. And let's join in thanking Sarit for everyone.
Thank you very much. Thank you, Subi. And thank you.
Thanks, Sarit. Please unshare. Yeah. So we'll move to the last presentation of this today's session, as well as this FCBS meeting, last technical presentation. So we have an NMR expert with us, Dr. Vinesh Vijayan. Again, he is well known to most of the audience here. So he's currently the associate professor from the Department of Chemistry, IISER, Trivandrum. He's a real expert in NMR spectroscopy, solid-state NMR, structural studies of small molecules and biomolecules, developing methods, new methods in NMRs, and so on. And he did his PhD from Max Planck Institute, Göttingen. And also he did postdocs from the real experts groups in solid-state NMR and biophysical from the Institute of Biophysical Chemistry of Max Planck. So with this brief introduction, let me invite Vinesh Vijayan to.
Hi, thank you, Professor Subi, for your kind introduction. Let me try to share this. Can you see the presentation now?
Yes.
Okay. Yeah, so in the outset, I would like to thank the organizers, especially Dr. Reggie, Joshi, and the rest of the FCBS members for giving me this opportunity to present. This is present a topic that I'm passionate about. So this is about fundamentals of protein NMR spectroscopy. So what I'll do is mostly a pedagogical talk. So if I have time, I'll go into some research part, but otherwise it is just going to be on the fundamental NMR spectroscopy. So so that introduction, I'll just go through what we are going to do, what we are going to discuss. So when we talk about NMR spectroscopy, we have to think about spins, right? So in the spin, we have the spin of first we should know what a spin is. A spin is, and especially a spin of an electron. Now, if you want to know the spin of an electron, the first question you have, what is the spin of an electron? And the answer, if I ask you that, though I can't see you writing, but you can answer in the chat box. If the spin of an electron, many of you write as plus or minus half. That is not actually the spin. That is, the spin of an electron is always half. So the first thing is, it is half. The spin of an electron is a quantum number. Spin quantum number is half. It doesn't have any plus or minus half. So what is this plus half and minus half? That is the spin states. The spin states. Now, how the spin of an electron and the spin states come about, that comes, the more knowledge about that comes if you look into the angular momentum, especially the orbital angular momentum of an electron. Now, in orbital angular momentum, you know that if you just take a d orbital, you have L is equal to 2. Small l is equal to 2. Then there are ml values which goes from minus l to plus l, minus l to plus l. So you have plus 2, 1, 0, minus 1, minus 2, right? And you have all those d orbitals, right? So you see that, but when we talk about L, the angular momentum L, the first thing is it's quantized. The angular momentum is quantized, and what is the relationship between L and ml? You know very clearly. It goes, there is 2L plus 1 ml values that corresponds to an L value, right? So what is it picturesque? How does it get represented? So the first, the important part of angular momentum is that it is a vector quantity. Angular momentum is a vector quantity, and it should have a direction and a magnitude. And the direction, this L here, the magnitude of that is given by this L value, the small l value. So what is that direction? So if you have a vector like that, the magnitude of that is given by root of L into L plus 1 h cross. Right. So that is the magnitude of the vector. Now, there should be a direction. Now, if you have a vector in a three-dimensional space, it should have both the y-axis. I mean, you should know the projection along x-axis. You should know the projection along z-axis. You should know the projection along y-axis. So if you know all these projections, we know exactly where this vector is pointing to in space. Okay, so angular momentum is a vector quantity and it should have a direction. So that direction is determined by the projection along x, y, and z axis. Unfortunately, quantum mechanics tells you that you cannot determine simultaneously all the three components of the angular momentum. This is the uncertainty principle. So what we can actually determine is the only the one of the component, that is we take it, meaning the only component that we can determine will be the z component. You can as well have chosen y component, or you can choose x component, but we have chosen z component. So you have the L, the magnitude, you can determine the magnitude, which is given by root of L into L plus 1 H cross, and the Z component. Z component will be ML H cross. Okay. Now you know the relation between the small l, this small l, and this ML. This small l, the ML values would be going from minus L to plus L, right? So if you have 2, L is equal to 2, then you can have ML value 2 H cross 0, minus 1 H cross, and minus 2 H cross. Likewise, spin here. Now we come to spin. Spin is also an angular momentum. Okay, a spin is also an angular momentum. Before we get to spin, you see that since we cannot determine simultaneously the X and the Y component, this vector here, which has this magnitude root of L into L plus 1 H cross, could be anywhere in this cone and will still satisfy root of L into L plus 1 H cross as well as this projection here. Okay, this projection here. So it will satisfy ML H cross and root of L into L1 H cross anywhere if this vector is anywhere in this cone, right? Okay, so this is where you have this cone picture coming into place. Now we come to spin. Now spin, as I told you, it's a spin angular momentum. S is equal to S being half. Now that is just is like your L. The S is like your L. Now what is then the plus half and minus half? Plus half and minus half are the MS or the spin states that I told you. Okay, so there it also goes from minus S to plus S with a difference of 1. So you have S is equal to half, so you have minus half and plus half. Okay, so here again you can see that this vector here, you can only determine the magnitude of that vector, that is root of S into S plus 1 H cross, as well as the Z component of the spin, that is half H cross or minus half H cross in this direction, because this is for the spin state plus half. That is why this vector is along the positive Z direction. This is if you have a spin, the spin state as minus half, this vector will be in the minus Z direction. Okay, so this is where these cone pictures come into place. So remember this cone picture because this is what we are going to deal with later. Okay, now when we talk about nuclear magnetic resonance, we have to talk about nuclear spin, and we have seen electron spin. Nucleus also have their own spin, but most importantly, for magnetic resonance, you have to put it in a big magnetic field. Only then the degeneracy, that the spin states we have talked about here, the spin plus half or minus half, that will have different energy. If there was no magnetic field, plus half and minus half will have the same energy. Just like there is 2L plus 1 degeneracy for your L is equal to 2 states, 2L plus 1 degeneracy for your L is equal to 2 state. Like here also you have 2S plus 1 degeneracy for your S half state. Spin half molecule, spin half electron, right? So if you want to lift the degeneracy, that means you have to lift that plus half and minus half spin states have different energy. You have to have a asymmetric field to put in. Okay, so what we have is a Zeeman effect, where if you put a magnetic field only in one direction, then the energies of the plus half and minus half will be different, and you will be able to observe NMR. So the important part of the thing about spin and how it interacts with magnetic field is it is interacting through the magnetic moment. So the spin angular momentum or any angular momentum has an associated magnetic moment is associated with the magnetic moment. So you have if you have the scaling will be different. The spins have a different scaling, or the orbital angular momentum have different scaling. So the spin scaling, that is S here, scale goes like this. Mu is equal to, mu is the magnetic moment, is equal to gamma S. So mu, the magnetic moment is directly proportional to spin angular momentum with the proportionality constant gamma, which happens to be the gyromagnetic ratio, which is based on the charge to mass ratio of your particle. Okay, so mu, the magnetic moment, this mu is what is interacting with your magnetic field and producing these energy differences, right? So so when it comes to nuclear spin, if you really want to understand or want to figure out what is a nuclear spin of an atom, you should know how they are, how the nucleons, that is protons and neutrons, are filled in the nuclear energy levels. But that we are not going to do. What we can, however, say is that if the atomic mass and atomic numbers are both even, then you have zero spin, and therefore NMR, there will not be NMR because there is no magnetic moment associated. If you have zero spin, there's no magnetic, mu will be zero, and therefore there will be no NMR. But if your atomic mass and atomic mass is odd and atomic number is even, then you will have a half integer, can be 1 by 2, 3 by 2, 5 by 2, etc. Then you will be able to actually do NMR. Okay, so if you have spin half, you will have two energy states, plus half and minus half. That will be the same energy. If there is no magnetic field, it will have different energy if you put it in a magnetic field. If spin is 1, there will be 2i plus 1. There are 3 energy states, minus 1, 0, and 1. If I is equal to 3 by 2, then 2i plus 1, 3 plus 1, 4 energy states. So it goes from minus 3 by 2 to plus 3 by 2. So you will have 4 energy states. So in our discussion, we will only deal with spin half nuclei. So because proton or the hydrogen nucleus is a proton, right? Hydrogen nucleus is a proton, so that has a spin half. So we will mainly look at hydrogen nuclei. We also look at carbon-13 and nitrogen-15. They also have spin half. So it's basically about spin half NMR. So what is the energy? I told you the magnetic moment is the one that is interacting. This mu magnetic moment interacts with the magnetic field, giving this energy. So how is the energy related? E is equal to minus mu b. If you go through the equation, it comes out that the energy difference between the plus half and minus half is gamma h cross b, and the frequency, that is delta E, the frequency is gamma b0. So if you have a frequency gamma b0, if the frequency is gamma b0, then you will be able to excite your spins from the lower state to a excited state. So what is this frequency? This frequency comes in the radio frequency range of the electromagnetic spectrum. Okay. Now the important part here in this figure is that the energy difference between the two spin states depends on the magnetic field. At 1.41 Tesla, for a proton gyromagnetic ratio, that is gamma of the proton, it is coming around 60 megahertz. Okay, so 60 megahertz would be the frequency that is required to excite nuclear spins from the ground state to the excited state at 1.41 Tesla. But as you go to 7.41 Tesla, that is around 300 megahertz, you will require much higher frequency, 300 megahertz, to excite the spin from the ground state to the excited state. So the frequency depends on your magnetic field and also gyromagnetic ratio. So carbon-13, which has only 1/4 the gyromagnetic ratio of your proton, will resonate only at like 20 megahertz. Okay, so what is it in the resonance? So this frequency that we are supplying, radio frequency, is required for the excitation of this. This is the one that is if the magnetic field is along this axis, and you have this vector pointed along pointed along this axis, then the radio frequency is absorbed and then it gets flipped like this. So this is a classic way of representing, but this is only representing one nuclei or one spin. Okay, but when we actually measure NMR, we are not dealing with just one spin. We have a large number of spins, Avogadro number of spins. So we are not actually flipping just one spin. We have to look at the ensemble average. Okay, so how does that work now? So these vectors here, you see these vectors are the previous vectors, but there are many number of them, right? Now there are more number in the positive x-axis, positive z-axis, because the population is mainly determined by the Boltzmann factor. So that means the ground state will be slightly more populated than the excited state. But however, since the energy difference is not that much, the population difference between the excited state and the ground state is not great. So they are almost, we can say they are almost equally populated. But anyway, the number of, as for representative purpose, the number of lines here is larger than the lines that is drawn towards the minus z axis. Now, what is important to realize is that this, just let's look at one of this vector here. Now, it has an x and y component, and also this vector here, that also has an x and y component. Now, this vector here and this vector here, the x and y component of these two vectors get cancelled out. But their z component, the z component, they get added up here. They get added up here, right? Likewise for this and this, this and this, they get added up. So all these vectors which are in this cone that we started off with, okay, all these vectors, because there are large number of your nuclear spins, all these vectors gets added up and you get the major big vector, big z component along the positive z axis. Okay, the xy component basically gets subtracted out. While here in the minus z also, you will have the same thing, that you will get a minus z component, minus mz component here. But this minus mz will be, this minus mz will be smaller than this guy, this positive mz. Why? Because the number of vectors in the ground state, that is pointing with the magnetic field, will be higher compared to the excited state. So a net result would be a vector along this direction. Okay, net result would be a vector along this direction, which we call the M0. The mathematics of doing that is given here. Okay, and this M0 is what is given here. We use the Boltzmann to find out what exactly, how much each of the orientation would be. So when you do the calculation, it turns out that this M0 depends on the n, the total number of spin. Basically, it's the concentration of your spin. Gamma, that is the gyromagnetic ratio, the magnetic field, and inversely proportional to your temperature. So what we actually detect in NMR is this guy here, M0, this blue guy here, M0. Okay, so that basically depends on your concentration of your sample. It depends on your magnetic field and inversely depends on your temperature. Okay, so if you want to increase the sensitivity of your NMR, you have to increase your magnetic field, or you have to increase, well, you have to increase the concentration or reduce the temperature. But temperature reduction has other problems that I can tell you later. So we are going to detect this M0. That's the major thing. So what we have right now, we have set up our NMR system by having the spins all aligned along the plus z axis. Your magnetic M0 aligned along the z axis. Okay. Now that is a problem. Now we have to, there is a B0 field along this direction. There's a B0 field and there is an M0 aligned with it. Okay. So they are like parallel to each other. Now we have to pull this M0 out to actually see how much of M0 is there. Okay, so we have to kick it out of B0 in order to observe. So what happens if the M0 goes out of the B0? It starts to go around the B0. Okay, there is a torque. So B0 is going to pull the M0 back. And so there is a torque that acts on M0 that is going to make it go around the B0. And that is what we call the precession. That is called what we call the precession. So, but first of all, we have to get the B0, we have to get the M0 out of the B0 plane. Okay, so how do we do that? And that's why that's one of the reason. That's actually the primary reason why Felix Bloch got Nobel Prize in NMR. Well, actually discovering NMR, how we can do it. So what we do is apply a radio frequency, which is, now we have to apply a radio frequency because that's the only thing which can interact with the M0, right? How do we have to apply? We have to apply a radio frequency perpendicular to your B0. So this is a radio frequency coil. We have to apply a radio frequency perpendicular to your M0. Oops. Okay, once you apply that radio frequency perpendicular to your M0, you see that the magnetic moment, which was here, has moved into the XY plane. Now the time required for once this magnetic moment comes from trace this blue path here, then you stop the radio frequency. Okay, then you stop the radio frequency. The time taken for this magnetization to come to this axis here is 90 degrees. This the time taken is the 90 degree pulse. Okay, because it is a 90 degree, right? This is a right angle. So you get your magnetization from here up to here. This blue the blue trace. The time taken for doing that is the 90 degree pulse. Now, if you don't stop here and you continue to do, where would the magnetization go? Magnetization will go down to the minus Z. Then you still continue pulsing. It will go up again to minus Y and then back on to Z. Okay, so it keeps on going around it if you keep on applying your radio frequency. But a 90 degree pulse is sufficient. I will tell you why we need to only do a 90 degree pulse, because you saw the magnetization going around the B0 field. Once the pulse is done, that is, you have the pulse, you have a 90 degree pulse. This magnetization goes from the Z axis and comes into the Y plane. Then there is nothing else other than the B0 field here. Okay, the radio frequency has stopped. Okay, so this is a 90 degree pulse. The magnetization has reached the Y axis. Now there is only the B0 field. Now, because of the B0 pull, it is going to go around. There is a torque that is going to make the magnetization go around it. Okay, it goes around the B0. You also see that it is going up. I'll tell you why it is going up. That is called relaxation. It has to come back to its equilibrium position, right? So it will return to its equilibrium position, going around, round, and comes back to its equilibrium position. You also see that if you look from the top, you see this movement of the magnetization going like that. Now, if you keep this radio coil there, what happens? This is a magnetic moment that cuts this coil here and creating a current, and that current is what we see here. The current is what we see here. So and the current is decaying. You can see that the current is decaying. Now you see a red and the blue trace. One is cosine modulation, the other is a sine modulation, because when you have a coil here, we keep another coil here, so we get both the cosine and the sine modulation. Okay, so so you see the current decaying. Why is it decaying? Because the magnetization is going up, so the XY component is getting reduced on the plane. So it is basically decaying also. So this is what is a free induction decay. What we see here is the free induction decay. It is an amplitude versus time delay. The induced current is being seen here. This is the free induction decay. Now that is of course not really useful for analysis, because we need frequency versus amplitude, not time versus amplitude, right? And how do you get that? We do Fourier transform. Now I told you how the whole the process, but here is the inner working. So you have this is a permanent magnetic field. You see the line of forces going like this. You have a probe with the radio frequency coil and the B1 field. The radio frequency is electromagnetic frequency, right? It has a magnetic component. The magnetic component is the one that is going to interact with your magnetic moment. Okay, so that the direction of that magnetic field will be perpendicular. So that lines of force will be perpendicular to this line of force. Okay, so that's how we get that. Okay, and when I say a pulse is a burst of radiation. That means you are applying a radio. There is absolutely no radio frequency, and for a short duration, you are applying a radio frequency and you stop it. Okay, and that's the time required for the magnetic moment to reach your XY plane. Okay. So, you saw that you have this signal, Now, of course, we have to digitize it, then feed to the computer, and then what we get is we have to do Fourier transform of it. Okay, Fourier transform converts any two reciprocal spaces. So time and frequency are reciprocal to each other. So you can simply do Fourier transform in order to convert a time domain signal into a frequency domain signal. Okay. Now you saw that the magnetization was going up after reaching the XY plane, right? And there are two types of relaxation. This is because they are relaxing, and there are two types of relaxation. One is the longitudinal relaxation. That is very simply put, it is the time taken for the magnetization to come back to its equilibrium position. That is the M0. So when you apply a pulse, it has lost magnetization. The M0 was the magnetization at the start, and that was aligned along the MZ, right? When you have a 90-degree pulse, there is no MZ anymore, because all of that is converted to either MX or MY, right? Now, the time taken for it to go back to its original position, this time is actually the T1 longitudinal relaxation time, or spin lattice relaxation time. Okay, so this is usually very long. Okay, this is usually really long. It's in seconds. It's in a few seconds. While the most important, and that basically determines the line width of your spectrum, is the transverse relaxation time. This is how fast this spins. I told you this. The bunch of this M0 is a bunch of nuclear spins, right? Nuclear spins that has bundled up. How fast those spins gets defaced in the transverse plane, that is given by the transverse relaxation time. This is also otherwise called the spin relaxation time. And you can imagine this like a bunch of sticks. You know, each of those vectors that are like bunch of sticks being tied together by a rope. Now, when you put it into the XY plane, you remove the rope, the sticks, the bunch of broomsticks, whatever, that gets spread out, right? That spread out. We call in NMR decoherence. Okay, it gets decoherent. So the time taken for it to completely dephase, that means it loses its memory of being together. That time is the transverse relaxation time. Okay, so, and that is called, and they do that because they'll be able to exchange energy between each other. So that is why it's called a spin relaxation time. And the line width of the spectrum depends exclusively. Why is that? Because this is much faster than T1. So the line width actually depends on your T2, the transverse relaxation time, 1/π/T2. If you have a long T2, you will have sharper lines. That is for most small molecules. But if you have proteins and all, you have short T2. That means it relaxes much faster. That its dephases much faster. You have broad signal. You can also see from the FID itself. You see a fast decay. That means faster relaxation. You have slow decay, slow relaxation. I told you about Fourier transform. If you do a Fourier transform, you get a real part and you get an imaginary part. And the real part of the spectrum is Lorentzian. You probably have studied Gaussian, but this is the Lorentzian function. The difference is that the Lorentzian functions are very sharp and tapers down pretty fast to 0. So you have the Lorentzian function, so you get sharp signals. Okay. And what we observe in NMR, or what we actually draw in NMR, is this the real part, not the imaginary part. Imaginary part we discard, but we need both real and imaginary for phase correction. Okay, so coming to the magnet itself, the magnet is a superconducting magnet, and that is immersed in a helium bath. Also, there is a hollow board that goes from the top to bottom, where you put your probe. This is where you apply your radio frequency. These knobs here gives you different frequencies. This is like our channels in radio. You have different channels, right? Radio FM 93.5 FM, 94.7 FM. Like that, you have proton frequency, you have carbon-13 frequency, you can have any other frequencies you want to. There are actually 4 frequencies here. So you can put it right inside. So this long tube goes up here. This is actually in the room temperature, not in the helium temperature, because this bore is there. Okay, the superconducting magnet or the coil are wound around the bore. Okay, and once it's charged, it's permanent. It's a superconducting magnet. It doesn't lose its magnetization until you don't do anything with the helium mass. Anyway, the sample goes from the top and lands in the middle of your probe and middle of your magnet here. Okay, so when it comes to signal, there are three important things in any spectroscopy, and that is the number of signal, position of peaks, and intensity. Okay, so we will deal each one of them. I'm not going to, the whole point of this thing is not to give you where exactly all the chemical shifts are. This is just to show that there is chemical shift. Now, what is a chemical shift? The chemical shift is because you have the nucleus is not naked. It is surrounded by circulating electrons, and these circulating electrons produce their own magnetic field. And normally, a diamagnetic field created by the circulating electrons opposes the applied magnetic field. So the field observed, the field felt by the nucleus will be less than the actual field. So the field supply is B0. So you have to subtract out the field basically from the circulating electron. That is given by sigma B0. Okay. So sigma is the shielding tensor or shielding. So gamma 1 minus sigma B0 would be the frequency. So previously gamma of the omega, the frequency was gamma B0. Now because of the electrons moving around it, that is creating the a magnetic field that is going to oppose the applied magnetic B0. This is subtracting out B0. You have this modified equation, omega is equal to gamma 1 minus sigma B0. Okay, and you can see it here. If you this is benzyl methyl ketone, and where you are at B0 at 1.41 Tesla. That is resonating frequency on the proton channel to be 60 megahertz, gamma B0 being 60 megahertz. Okay, so you're supplying 60 megahertz. You can see this methyl is coming at this frequency, the methylene comes at this frequency, while the hydrogens on the benzene ring comes at this frequency. This is a quite high frequency because that is quite de-shielded, right? Quite de-shielded. It's like the electrons are no more there, de-shielded. While here the methyls, it is well shielded. It is the 60. It is little far away from 60 megahertz. 59.99700 megahertz is slightly. Though it is, if you look at the absolute numbers, it looks very small. But you remember this is megahertz. If you put it in hertz, it's still a significant amount, right? So you see that the differences are really small, and that differences is what is chemical shifts. Okay, so chemical shift is if you have a shift in frequency divided by the spectrometer frequency in megahertz, then you get ppm parts per million. Just give the number as parts per million. Okay, so you don't, you should not, you should multiply by 10 raised to 6 if you're actually having megahertz in. Right. So in order, you should also know that the omega depends obviously on a magnetic field. So at different magnetic field, you will have different frequencies. So same sample measured at different frequencies will give you different spectra or different frequencies. So in order to standardize that, we have to have a reference, and normal references that is soluble that we use, which is soluble in organic solvent, is tetramethacylate, and we give the delta ppm value to be 0 for TMS. So the delta is defined as nu, the frequency of your interest, minus the nu TMS, the frequency of your TMS signal, divided by nu TMS. Now nu TMS is in megahertz, so you have a 10 raised to 6 on the bottom. So you have to multiply by 10 raised to 6 to get the delta ppm value. So this scale is the delta scale that we have normally for proton NMR or hydrogen nuclear NMR. It goes from 0 to 10 generally. As I told you, this is not my interest to give you exactly where the chemical shifts lie, but just to, for the sake of completeness, I will say that the methane, which has all the electronegativity between hydrogen and methyl carbon is very less, so it comes around 0.23. Carbon, hydrogen, and silicon is not great. So I mean, they are almost same. So it comes very close to tetramethacylene. If you replace this hydrogen with the bromine, it comes at 2.68 ppm. You replace with the chlorine, more electronegative, 3.05 ppm. You replace it with the fluorine, it becomes 4.26 ppm. So as you see the electron being withdrawn away from the hydrogen, the chemical shifts are shifted to the higher ppm values. Then about the number of signals. The number of signals depend on the different types of protons in the compound. So for example, this ether compound has CS3O, CS3. They both have, they are related by a C2 axis. So both of them are highly symmetric. So these hydrogens are have the same chemical shift. They don't have any differences. While for this molecule, the CH3 and the CH2 will have two different signals, because this CH2 is directly attached to a chlorine, this CH3 is not. So the chemical environment around here is different, is going to be definitely different from CH2. So like that, you'll be able to, so different, if the molecules have, if the hydrogens are in different chemical environment, then they will give you different signals. That's the whole point. Here again, if you have CH2, CH2 highly symmetric, so both of them have the same chemical environment. So you have the same signal. But if the Cl was replaced with the bromine, then there is an asymmetry. So this and this hydrogen will have different chemical shifts. Okay, now it comes to splitting. Till now we have talked about a single absorption signal. Now just look at this compound here, CH2, CHBr2. We expect two chemical shifts. These two hydrogens, because they are attached to one bromine, and this hydrogen, this is more de-shielded because there are two bromine attached to it. So we can say this guy, this signal is from this hydrogen, and this signal is from this methylene hydrogens. So this methane hydrogen, you can see that it is split into a triplet, while this methylene hydrogen is split as a doublet. Now, what is the reason? Now, that's because these hydrogen, the spins of this hydrogen is coupled to the spins of the methylene hydrogen is coupled to the spin of methane hydrogen. Okay, and this coupling is called a scalar coupling, and that is through bond. This is what we call a vicinal coupling, they are usually 10 hertz or something like that, maximum. And what does that do? Basically, the population or the intensity is based. The energy is being influenced. Now, what is a coupling? A coupling means the energy of one state. And coupling in any sense means that the energy of one molecule is being influenced by the energy of the other molecule, another particle. Okay. So here, if two spin states are coupled, it means that the energy of the first spin is being influenced by the spin states of the second spin. You know that we are talking about plus half and minus half spin states of hydrogens here, right? So hydrogen coupling. So what we see is that if you have a signal of interest, let's say, which was not coupled to anything, now you have a coupling. Okay, you have another coupling. Now the second spin can be in the plus half state here, and it can be also in the minus half state. If this signal is coupled to the plus half state, then it will have a different signal. Okay, it will have a slightly shifted signal from the O, because they have, now it is going, because this plus half is influencing the magnetic field felt by this signal here. If this signal is coupled to the minus half state, then it will have a reduction in frequency. So you will get a signal away from the original frequency. Now we call this difference between the two splitted signal as J hertz or J scalar coupling. Second spin. Now this is always, this is actually set up by the molecule. This is not set up by the magnetic field. So it is independent of magnetic field. So you can actually calculate all this J coupling theoretically also. If you have just one neighbor, you will get a doublet like this. If you have one neighbor, you get a doublet like this. Now, if you have two neighbors,
Is okay? Vinesh?
Yes, I got logged out.
Yeah, I think all of you got hanged actually. I think the host is you only, right?
No, I'm not the host. It
Okay,
came
but
back again. I'm host now.
No, now it's okay now.
I'm a co-host. Fine.
Yeah. No, you just.
Okay. But are you able to see?
We can see you now. We are not at. We cannot see your slides yet. You have to share it again.
Okay. Where is it? I don't see it now.
You cannot see. Yeah.
Can you see now?
Yeah. Perfect. So Vinesh, you have like a 10.
Where did you lose it? I don't know.
Yeah, you have 10 minutes. Okay, Vinesh. Yeah.
15 minutes.
10 to 15. Yeah.
Yeah. I'll just quit. Done. Okay. So when I what I was saying is that you have you have three of this, two of this one having the same energy. So that means the intensity that you're going to observe will be twice as these two guys, because there are two of them here, right? So that is what. So you get 1:2:1 ratio. Remember, the original signal is being distributed in these three. Okay, not that we have created something. This original signal, if it was not there, if there was no coupling to a two spin, then the signal intensity of the original one would be much higher. But since it is coupled, now this original intensity is being distributed into the coupled signals. Okay, so like that, and the hertz is calculated like this. You get a 1:1 split. Likewise, you can go on. The intensity of the signal also depends on the intensity of the signal, or the area under the signal is proportional to the number of absorbing protons that you probably have figured out. So for example, I give you this example where you have C9H10O2 molecular formula and you have three signals. Now, if you take the integral, that is area under the curve, you get 54, 23, and 33. So there are 10 hydrogens giving you these numbers here. Okay. So so if you add up 54, 23, 33, that should correspond to 10. So 54, 23 plus 33, that is the total number of integrated units, should correspond to 10 hydrogens. So one hydrogen, how much it corresponds to? It will be 110 units divided by 10 protons. That will be 11 units for one proton. So for this signal, especially if you divide 54 by 11 units, that will be around 5. So there will be 5 protons under this peak. There will be 2 proton, because 23 divided by 11, that will be around 2. So 2 proton here, and 33 divided by 11, that will be 3 proton here. So you will get 5 hydrogen, 2 hydrogen, and 3 hydrogen corresponding to these things. You can see C5H12O, C5H12O. There are only 2 signals, and you see that the ratio, the signal between them is 3. So the number of hydrogens is thrice here. Number of hydrogen that is here is thrice here. Okay, so there are 12 hydrogens. So the best bet would be a 3 and a 9. Okay, a 3 and a 9. Very easy. And from the molecular formula, you should know that it will be like methyl tertiary butyl ether. Okay. So in carbon 13 NMR, you know that it is going to have very small abundance, because we have only carbon 12 is odd mass and odd atomic number, so the spin is 0. But if you have carbon 13, it is spin half, and we should be able to observe, but it's only 1.08%. And of course, I told you 1/4 of carbon. The gyromagnetic ratio is 1/4. The magnetic moment is 1/4. So the sensitivity is smaller. Okay. There is, of course, 13C1H coupling that is there. And so you will get the splitting if you don't do decoupling. So you will get such complicated spectra. If you do decoupled spectrum, the decoupling meaning what is basically happening is it's just like the inverse of the what I've told you about the coupling. Now C13 should not see what is the spin state of proton. How do you do that? You apply a 180-degree pulse on the protons, 180-degree pulse. So that means you are inverting the plus half and minus half state So interconverting plus half and minus half state of proton. So the 13C will not recognize which state it is coupled to, whether it is plus half or minus half. Then what it does, it comes into the original chemical shift position and it will not be coupled to each other. So when we do that, so when you acquire the carbon-13, when you do a 90-degree pulse and acquire the carbon-13, you do a decoupling on the protons. 180, 190, 190, it keeps doing. So what you get, no coupling on the protons. So you get such a neat spectrum. Now there is carbon-13, I told you, is highly insensitive. Now we can, as pulse programmers, we can actually increase the polarization or magnetization on the carbon using inept sequence. Okay, what is called insensitive nuclear enhanced bipolarization transfer. That is taking the magnetization. It's like taking the magnetization of the rich guy, proton, and giving it to poor guy, carbon-13. So you can use a series of pulses interspersed with delays to really focus the magnetization to flow in one direction. Okay, and that is possible. And we see that the inept carbon-13 signal is much higher compared to a normal 13C signal. Okay, so that's because the proton magnetization, because the gamma of proton is 4 times higher, right? That is being given to carbon-13 now. So you can increase the sensitivity. This only works if there is a coupling between them. Okay, if there is a coupling between them. If there is no coupling, there is no inept happening. So quaternary carbon will not give you an inept. So depth is very similar to inept. Only thing is there is a 90-degree at the end, a pulse at the end on the proton, which basically determines whether you see a methane, methylene, or a methyl. Of course, the quaternary carbons will not have any depth because, as I told you, there is no inept there. So they'll be blank. But methane, if you have a depth 90, if the last 90-degree pulse is a 90-degree, you get a positive signal. For a methylene, methylene and methyl, there will be 0 signal. But for depth 135, you get a negative signal for a methylene, CH2, and you get a positive signal for methyl. In this way, you will be able to distinguish between methane, methylene, and methyl. Okay, so if you get a depth 90 signal, that means it will be a methyl. If you get a positive signal in if you get a negative signal in depth 135, that means it's a methylene. Okay, and methyl signal is if you have a depth 135 positive signal and no signal in depth 90. Okay, so when it comes to multidimensional NMR, multidimensional NMR is a series of one-dimensional NMR. The only difference is it's a very simple thing. You measure a series of 1D where you vary the distance between these two pulses here. This is a 90-degree and this is a 90-degree. You did it. This is a very simple 2D NMR experiment. If you vary these distances, each 1D experiment, the difference between each 1D experiment is a delay between P1 and P2. What you get is that your intensity of your signal gets modulated by this delay. So you get a second dimension. You just take the intensities of each of this signal. Fourier transform, take the intensity, and that will be another FAD. That will be another FA. Fourier transform that, and that frequency will correspond to the frequency that is happening during this delay, how it is being evolved in this delay. Okay, so that is how 2D works. Now you can extrapolate to 3D and 4D and 5D and things like that by multiple pulses. So people have done that also. What you get in Fourier transform is like this. You get a hill like that. And if you do a COSI, like what we have said, usually there is a diagonal peak that corresponds to the same frequency during this is called the mixing time. Okay. If they have the same frequency during the mixing time, they will come as a diagonal peak. But if they have a different frequency between the mixing time and the direct time, then there will be a cross peak like this. Okay, so a cross peak is these small peaks here. Diagonal peak is like this. Now normally we don't represent like that. We represent as contours like this. So you have a diagonal peak like this, and there is a contour peak in this direction. So what does this mean? This means that this peak or the spins corresponding to this peak and spins corresponding to this peak are coupled to each other. Okay, so you get a cross peak if there is a coupling. It can be any coupling. It can be any magnetization exchange happen. Okay, it can be any magnetization. It can be a coupling due to couplings can exchange magnetization. Chemical exchange can exchange magnetization. Okay, so all this is possible. So this is for the Cauchy pulse sequence, and here is a glutamine amino acids. You can see the H alpha here. This is an H alpha high shift here, and it's coupled to this peak here. That will be the H beta. So you should be able to see that it is not coupled to this hydrogen. This hydrogen here, that's because there is this hydrogen here. Okay, so this hydrogen is the H alpha here, that is coupled to this hydrogen here, and where is that hydrogen? And that hydrogen will be here, because you can see the cross peak here, not here. Okay, if these two guys were coupled, then you should see a cross peak here and here, which is not there. So you can see that you can walk along using a Cauchy spectra in amino acids and things like that. You can also increase this inept using one more inept step to make HSQC, and you get spectra. You get really highly sensitive spectra, because you are now detecting you're starting magnetization from the proton, and you're actually detecting on the proton. So here again, this is a Cauchy version, Cauchy-like, but it's heteronuclear. That's the only difference between HSQC and Cauchy. Also, we only see the cross peak and not the diagonal peak. So whatever peak that you see in HSQC spectra is other cross peaks. Now this is for butanol, and you see there are 1, 2, 3, 4 hydrogens. So you see the 4 hydrogens, and of course this hydrogen, for carbon. So you see 4 signals, which is a coupled to hydrogen. So only in the HSQC spectra you can only see carbons which have hydrogen attached to it. Now I come to proteins, and you see proteins have this problem that it's large number of hydrogens, large number of spins, and so forth. You have to identify each spin in order to do NMR. Now, first thing we have to understand where what is the important part, which is the peptide bond here. So NHCO region. Okay, so each amino acid, if they combine when they combine, they make a peptide bond. So there is an NH associated with it, except for proline. So that is one thing. Now, how the workflow for structure determination happens is you first have a sample preparation. That is basically a molecular biology work. You then do NMR spectroscopy, then structure calculation, analysis and structure calculation. So you have to do a protein expression. So you have to have your bacteria expressing your protein, and when the bacteria expression medium, we actually add carbon-13 glucose and 15N ammonium chloride, so that the bacteria uses carbon-13 of the glucose and the 15N of the ammonium chloride and incorporate them into the protein of your interest. So all your carbon-12 will be replaced by carbon-13. All your 14N will be replaced by 15N into protein. So if you take a ubiquitin, this is a small protein of 76 amino acid. It's really crowded. You can see that it's really crowded. And how to reduce the overlap? You have to do multidimensional NMR. So first thing is we measure an HSQC, but this is not carbon-13 proton HSQC. There will be a 15N proton HSQC. You see all these dots here, right? Now the issue is that now these dots are quite nice. It's like in your the skits book, you have so many of these dots, but there in those dots you have numbers given, so you can actually go around joining the dots and then finding out what is hidden in those dots. But here we have to find the numbers. Okay, we have to find the numbers. Now, how do we do that? We have to do the what we have is only the primary amino acid sequence. That means we know which amino acid comes first, second amino acid, third amino acid. That is the knowledge that we have. Okay, so that is what we have here. But there is also another problem. If let's say there are only 20 amino acids, multiple times you can find one amino acid in your sequence. So for example, this alanine is here and there is also here. So this is between two lysines and this is between phenylalanine and a glycine. So just identifying the amino acid is not sufficient. We have to identify which is behind or what, which is ahead of it and things like that. So that we have to also identify. Okay.
Vinesh,
so these are the problems.
Vinesh,
Yeah,
I'm sorry to
5 minutes.
interrupt you. Yeah, I believe you already closed your it's already 7 o'clock. You try to finish it so that you can take a couple of questions.
Okay, I started at 6. Okay, so we have to do first amino acid identification, which leads to knowing which is behind and which is ahead of it. And for that, what we have to do is do multiple experiment, 3D experiment, where we specifically transfer magnetization to its previous amino acid and to its own amino acid from the amide NH. Okay, so once we that NH that you have seen in the HSQC, we transfer magnetization to C alpha and C beta. C alpha and the C beta are very characteristic of each amino acid. So each amino acid has characteristic chemical shifts for C alpha and C beta. So we'll be able to identify them. Now we use this idea about HNCA and all these bulk sequences in order to see which amino acid behind and which is ahead. So what we have is a lot of, I'm going to skip all this, a lot of a puzzle which we then solve in order to identify each of these amino acids. So for example, this one is a leucine 67 and this is glycine 47, like that. So each of these dots we will be able to identify. Now, for 3D structure, you get something like that. Now, once you identify the dots, you know it's a fish, right? Now you have a fish, but now we don't know whether it is a mackerel or a sea fish. Now, how do you figure out about that? Now you have to have much more resolution and where these are actually placed. Where is the fin placed? Where is the eye placed? And things like that. Now, how do we do that? We use NOEs. NOEs gives you distance. So it's like a COSY spectrum. But the cross peaks actually is because of dipolar coupling. And if you see a cross peak, that means the distance between the two nuclei or the two nuclear spins is less than 5 angstrom. So using that information, we will be able to figure out whether it is a mackerel or a seerfish and things like that. So you get a thing. But all of this, of course, takes a lot of time. And of course, one does the structure calculation using molecular dynamics simulation, which using simulated annealing protocol, where we heat the molecule to a very high temperature and then cool it by adding restraints in it, which are these are the restraints: NOEs, J coupling, residual dipolar coupling, chemical shifts, all of that, which then we get a bunch of structures which satisfies all our experimental design, and that is what the model of a molecule would be. So when we start off a molecule, it will be completely before the starting of the molecular dynamics, we have a completely linear molecule. After we putting all the restraints, it kind of folds out. Okay, so basically, this is what we want to say. I guess I don't have time to go further into details. If there are, also I would like to thank you for the time. I think I have taken a little more time. What is it?
And
yeah,
sorry,
I just about finished.
It's 1 hour. I'm like,
can you hear me?
Sorry.
Yeah,
I can hear you.
I'm done.
Yeah. So we'll so that we can take a couple of questions. Thank you for a very clear kind of presentation on various techniques in NMR. So I can see that there is already a question in the chat box from Akshay Subramaniam. Can you tell about the difference between head-core direct technique and HSQC?
What is it?
Can you see that was head-core direct technique and HSQC?
Let me. Now I can see the chat. Let's see. Head-core, HSQC and
between head-core direct technique and HSQC.
Okay, between head-core direct technique and HSQC. Okay, head-core heteronuclear correlation is normally used in solid-state NMR, but it's an HSQC. It can be anything correlating a heteronucleate to proton. Basically, that is a head-core. Okay, so that was the original thing. Then heteronuclear single quantum coherence, that is HSQC. is made, which is very specific, that it is a single quantum coherence that is being evolved. Now, head core can be a multiple quantum, triple quantum, anything of that sort. Okay, so hetero correlation. Head core is hetero correlation. That means what is hetero? Here is a proton and a carbon-13. If you have proton-proton, that is a COSY spectrum, that is homonuclear. Okay, homonuclear correlation. Heteronuclear correlation is like a COSY, just like I said about HSQC, like a COSY, but very general term for HSQC, HMQC, and things like that, HMPC, and things like that.
So we can take one more question, that Omar Hisham. How does high pressure NMR help in studying minority conformations of proteins?
Well, if you apply any pressure or temperature, everything, you probably are disturbing it from its equilibrium equilibrium position. That means equilibrium energy state. So you're going to increase the possibility of detecting higher energy state molecules. Okay, and the population of the higher energy state molecule will be higher now, and then that will be able to be detected. That is why high pressure NMR and things like that. But the problem is, even, I mean, you can do high pressure. You need to have a high. You have to have a tube which is sufficiently able to handle high pressure things.
Probably one last question from Asha. So how you carry out the decoupling?
How do you, so can you explain how decoupling is carried out? Okay, so decoupling is carried out, as I told you, the coupling is the coupling or the splitting in signal is because there is the signal of your interest actually sees the state, or at least are coupled to the spin state of its coupled partner. Let's say if I have I am the spin half, I am a spin, and then I'm coupled to a spin half nuclei. So that will have a plus half and a minus half state. Okay. Now, if I don't see what is the spin state of my coupled partner, if I don't see, meaning if I don't know what is the spin state of the coupled partner, then I will be in my own chemical shift. I will not move ahead or below. I mean, I will not change my position. I will not be go with the plus half state or minus half state. So what we do in decoupling is basically to confuse your signal of interest by applying 180-degree pulses to the coupled partner. Okay, so in carbon-13 proton decoupling, what we do when we detect carbon-13, so you do a 90-degree on carbon. So you have a magnetization of your carbon, and you put it in the XY plane. As it goes around it, we decouple. We put 180-degree pulse on the protons. So there are two channels. They will not see each other. Okay, because carbon-13 frequency. Let's say if you have 400 megahertz proton frequency, the carbon-13 frequency would be 100 megahertz. Okay, so they don't see it. So you have a carbon-13 which is moving around at 100 megahertz. Your decoupling going at 400 megahertz. Okay, very fast, and that is going to confuse the carbon-13 signal. That the carbon-13 signal will not see whether it is attached to a plus half state of the hydrogen or the minus half state of the hydrogen. 180-degree, because you have what is a 180-degree? It is basically flipping your plus half to minus half to plus half. That is what we are going to do.
Yeah, thank you, Vinesh. I think considering the time, we should stop this discussion here. But I can see that you have generated a lot of interest.
Thank you very much.
You have generated a lot of interesting questions. Probably you should think about a part 2 of your NMR class at some point of time. Okay. So thank you once again, Vinesh, and all the speakers of this session. And thank you once again. I give back to Joshi or Dr. Das.
Yeah. Thank you, Dr. Subi. Thank you for. I hope that you can hear me.
Yeah, we can hear you.
Yeah. So thank you, Dr. Subi. Thank you for conducting the session so well. I'm sure that all those who are present here will agree with me that we have had a fascinating series of lectures in this session. I can see from the feedback that we have got there, that there is a lot of appreciation, and there is a wide variety of talks, from pedagogical explanations to the actual applications and research, high-end research that is being done. So this is the kind of variety that we like to have in the FCBS, and if you would have seen in all those 3 days. Of course, the organizers, Dr. Joshi Joseph, Dr. Subi, and Dr. Reggie have given me 15 minutes, but I think it is quite late in the day for me to, and we have already had 3 long lectures, and people have been patiently waiting. So I hope, I don't think I want to keep you here too long. But of course, it is my pleasant duty now to thank a lot of people who have made this happen and made it successful. You know, in the first day I had said that the main aim of this workshop is to bring together students, teachers, researchers, and mentors under one roof. Unfortunately, due to the pandemic, this was not possible. In fact, we even had a doubt whether we would be conducting this FCBS this year, but it is only because Professor Rao insisted that we should not have a break, whatever the situation that his encouragement is what made us do this online. And I am very happy to see that in spite of the fact that it was done online, we had a very good participation. The students, large numbers still present, even in the last day. Of course, the credit is to be given to all the speakers. So I take this opportunity to thank Professor Rao, who has been a constant supporter for this FCBS and encouraged us. And I'm sure that with his support and encouragement, we can improve the quality of these FCBS workshops in times to come. Of course, during the next year, I'm sure that we will be doing it on a face-to-face basis. I would also take this opportunity to thank both the directors of CSIR-NIIST, Dr. Ajay Ghosh and Professor Murthy of IISER, for the support, for the strong support and also the infrastructure facility that they have provided. And much of this, of course, the fact that we have contact of all these students would not have been possible if it was not for the help that we received from many of these teachers with whom we have had very long-standing interaction, like Professor Jem Matthew and Dr. Joby Thomas, and also Dr. Bashir. You know, they have been very, very supportive. I also take this opportunity to thank all the resource persons. We can see how much, how passionately they have been doing, they have been giving these talks. It's not easy to give an online talk and keep the attention of people over this period, but the commitment of the speakers is clearly seen, and that is what that is why I see that we still have such a large number of participants still attending at such a late stage. So on behalf of FCBS, I take this opportunity to thank all the resource persons for the extremely wonderful way they have prepared and delivered their lectures. And of course, none of this would be successful if it was not for the participants and also their interaction and the active participation of this. In spite, as I said, again, we had problems of being online in spite of that. And I think one of the things that was, many of you would have heard, is that Dr. Joshi Joseph and Dr. Reggie Varghese and Dr. Subi had mentioned continuously that if you have any doubts, if you feel you would like to have, not just for your science or any aspect, you can always contact these resource persons, and I'm sure that they will be very happy to help you. So I, again, on behalf of FCBS, I acknowledge the strong participation from all these students and teachers. You know, as I have been saying again and again, that doing this online has not been easy, but I think Dr. Joshi Joseph, Dr. G. Varghese, and Dr. Subi George and Dr. Balasubramanian from different institutes have cooperated, coordinated, worked with enormous cooperation with each other. I've been watching that. It is really wonderful. And that's what made it all possible. And it all went so smoothly. I'm very happy. I should also mention Dr. Vinesh Vijayan, of course, who was silently working behind lines to make sure that everything that we were doing online went smoothly. So I take an opportunity to thank all of them. Once again, I hope we will, next time, of course, I'm sure that we will have this face-to-face. I look forward to that. And I think with this, I would like to conclude. I take this opportunity once again to wish all of you a Merry Christmas and a Happy New Year. We are almost coming to the end of the year. And I look forward to seeing you all in the next workshop. So thank you, everyone. Bye. Joshi, unless you want to say something that you can.
Joshi, Joshi, there was a question whether they will have access to the recorded lectures.
Yes, all the lectures are recorded and it's available in YouTube. I have shared the yesterday's and day before yesterday's YouTube links, and today's also I will post it in the WhatsApp, and you can like it will be there for some more time, so you can watch even if you missed some of the lectures, you can watch it. And we probably will be keeping it in that YouTube channel for some more time. So it's available.
Okay. So anybody wants to make the last word and say goodbye?
The yesterday's and day before yesterday's YouTube links, and today's also
Joshi?
in WhatsApp, and you
can have the last word, Joshi.
Like some more, so you can. Sir, I'm hearing my own voice now. I don't know.
I think connection has from our side, connection is a little bit unstable.
I think probably you are listening to YouTube streaming, then it is coming little late. Probably that's all.
Oh, that's
Okay.
true. Yes. I just clicked on that because I wanted the links. Thank you all, and see you all next year. Subi?
Yes, we missed the residency towers.
Okay, we will be.
We will do that next year, definitely.
Okay. Thank you all.
Bye.
Okay, so thank you. Bye bye.
Thank
Subi,
you. Bye-bye.
good night.
Bye. Thank you.
Raji.
Okay, Joshi, we will meet you soon.
Dinesh, actually, it was very good lecture, and I know that NMR is cannot be summarized in 1 hour, and I hope the college teachers listening to it will take your expertise for their benefit.
Yeah, Vinesh, we will also invite you to give. You should give some special lectures to our students. We will probably arrange. It's like kind of nicely covered.
I think they already.
I thought I messed it up.
No.
No, that's great. Even for me, you know.
Mahesh and all are arranging.
I was not in a good mood. That's why.
It's very good.
Starting trouble.
So we'll have to get him in a good mood.
I should have been a little more faster.
No. I know how difficult it is to explain the fundamentals of NMR.
Yeah, when I start, I had planned everything. But when I see the slide, I add more.
Yeah.
Lectures to our students, we will probably arrange. It's like kind of nicely covered.
I think they already.
I thought I messed it up.
No,
that's great. Even for me, you know.
Mahesh and all are arranging.
I was not in a good mood. That's why.
It's very good.
Starting trouble.
So we'll have to get him in a good mood.
I should have been a little more faster.
No. I know how difficult it is to explain the fundamentals of NMR.
Yeah, when I start, I had planned everything. But